And away we go. Welcome to APEC, everybody. It is January 17th, 2026, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody who was watching us on YouTube. Let me take a look here. Facebook, LinkedIn, Twitch, and X. So we are streaming live across several different channels. So today I am really pumped up. Giovanni Cambria will present on the relativistic amplification of the engineered quantum vacuum. George Egely will survey the current state of LENR, also called cold fusion, through the lens of catalytic fusion. Orestis Lazanakis will be discussing the results of isotope tests conducted on purported ET material samples. And Larry Deavenport will be discussing his hands-on replication of the Townsend Brown FlameJet generator. So we have a lot going on. We're also going to have updates from our lab partners, and we're going to finish off the event with some open discussion. So today's event uses StreamYard. Again, we are multicasting, but the primary channel is our Alt Propulsion YouTube channel. If you haven't subscribed to that, please do so now. You can ask questions using the live chat feature on the right-hand side of the page. We will try and get to those. They do scroll up the page pretty fast, so we're not always able to. But depending on time constraints, depending on how things go, I try and work some of those in as well. And you can always view conference replays, details, and speaker info on our website at altpropulsion.com. One thing to add there, I have been adding stories and breakout videos on notable past presentations. We have too many to add them all. Believe it or not, this is, I believe, our 82nd or 83rd conference session. And so what I've been doing is selectively going back through, finding notable presentations, uploading those as single videos, writing really good descriptions, sometimes stories, trying to get all of that material up there. And the goal there is learning and education, right? There is so much that we can learn from the amazing people who have presented here. So I am going to get started now. I'm going to bring in our first presenter, Mr. Giovanni Cambria. Giovanni, welcome and thank you so much. Thank you for APEC, man.
Thank you so much, Tim. Thank you to all the audience. My name is Giovanni Cambria. I have a master degree in computer science and a background in physics. I studied physics at the University of Pisa. Then I moved to computer science. And that's my presentation. It's a work about negative energy density amplifications. With the slide, you have all the information you need to fully understand the physical principle we are talking about. So my presentation is sometimes a bit fast. Some details are not covered completely, but on the slide you have all the information you need. So it's important to have the slide in the archive.
Yeah, and Giovanni, let me add that now. So now we're on slide 1, so folks can see it. And you also, just so for the audience, you have a video presentation. I'm going to try and download that and upload it to the YouTube channel as well. But if you're cool doing this live, I would love to have you walk us through it. And it is up. Just tell me when you need the next slide. Just say next slide, okay? And I'm going to remove myself.
Perfect.
I still hear you.
When I need the next slide, I will say next slide. The physical principle we are talking about is quite simple, is take a little negative energy density and accelerate it along a toroidal track at speed nearly equal to the speed of light. So it's done without motors, without moving parts, using only a lasers and a EOD, an electro-optic deflector. So it's like a particle accelerator, but without particles. Everything is done with negative energy densities. A little note, quantum equivalence principle, that avoid these create problems in this configuration are not applicable here, since the system is not static, it's not free space and it's not isolated. So quantum equivalence principle cannot be applied here. So we are free to go with our speculation for now. Ok, allora, my proposal is an experimental proposal to generate and amplify negative energy density for gravitational application. Next slide, please. To navigate this complex topic, I have divided the presentation into 5 main sections, 1 introduction and 4 main sections. First, we will start with the introduction, establishing the physical principle we are relying on. Second, we will look at the full presentation, covering the specific technology and the critical engineering constraints. Third, we will dive into the laser optics, the art of the amplification system. And finally, we will discuss the roadmap for application from gravitational wave generation to propulsion. Next slide, please. So let's begin by defining the core problem we are trying to solve. Next slide, please. We are all here because we share an interest in warp drives. However, while general relativity mathematically allows for superluminal travel, it imposes a formidable physical barrier. As proven by Ken Holum and later by Bobrick and Martyr, any geometry that allows for faster light travel violates the energy condition. It strictly requires negative energy density, or colloquially negative mass. For decades, this requirement has relegated warp drives to science fiction. My work accepts this constraint but reframes the question. Is it possible to engineer this negative energy density in a lab? Okay, so we now can see that in general relativity, in order to have warp drive, you must violate weak, dominant, and null energy condition. That's all about in this slide. Next slide, please. If we assume we can create a negative energy, how does it interact with the Earth? There are 2 competing models. The first is the Bondis model, which suggests that positive mass attracts everything, while negative mass repels everything. This leads to paradoxes like runaway motion. The second is bimetric gravity, or likes attract, opposite repel. In this framework, positive attracts positive, but positive repels negative. Actually, we rely on bimetric gravity, and we will explain in a moment why. Next slide, please. Do we have any evidence to support the bimetric model? We believe we do, in the mass defect. Atomic nuclei weigh less than the sum of their parts due to negative binding energy. High precision tests suggest that this negative energy component interacts repulsively with the Earth's gravity. Our conclusion is that the behavior of matter is consistent with the bimetric model. Earth's positive mass will repel a concentration of negative energy. This is the key to the anti-gravitational lift we will talk about in a minute. Next slide, please. This is a comparison between a standard particle accelerator and our device. It's almost a self-explanatory slide. The only point I wanted to stress is this. If we take into account the power expenditure related to gravitational wave emission, the energy needed by our device escalates as gamma to the 4th. So it's no more merely constant as is written here, but it escalates as gamma to the 4th. Gravitational wave emission is not needed, not related in any fundamental way to our device. It's possible to conceive a variation of the device without gravitational wave emission. Next slide, please. Okay, next slide, the second time. Now let's move to the experiment. The experiment is housed within a 60 centimeter circumference toroidal track, designed for continuous relativistic circulation of the activation point. So the activation point should move around in this track. The active medium is constituted by nanostructured solid gold nanorods embedded in a rigid ceramic titanium dioxide matrix. The nanorods are aligned tangentially. So you have these nanorods aligned tangentially along this track. Next slide, please. These bring us to the design of our engine. Here you see the initial state or the passive condition. In this state, even without laser activation, the vacuum fluctuations are confined within these tiny gaps. This generates a static negative energy density due to the Casimir interaction. So let's move to the next. Let's put a number on this passive state. Using the proximity force approximation for cylinders derived from a previous work on Casimir interaction, we calculated the energy density within the 10 nanometer gaps. The result is a static negative energy density of about -10 at the 4th joules per cubic meter. This confirms that our system, even when switched off, naturally resides in a negative energy state. But as I mentioned, this is static, is too weak for any kind of application. We need to increase locally this negative energy state. So next slide. Okay, so in order to increase locally the negative energy state, we fire with the laser to the toroidal track. The rotor is locked. The stator laser fires continuously at a single fixed sector of the ring. When the laser intensity exceeds the threshold 100 megawatts per square centimeter, and we are operating at 5 gigawatts per square centimeter, the metamaterial undergoes a topological transition. The isofrequency surface changes from closed ellipsoid to open hyperboloid. Unlike the weak Casimir effect, the resonant interaction with the Fermi gas amplifies the effect by the Purcell factor. The net energy density is deeply negative. What I want to comment here is that when you fire at a specific section inside the torus, the negative energy density in this specific section becomes more negative, so its absolute value increases. Next slide, please. This is not just theory. It has been proven experimentally. Krishnamurti in his science paper demonstrated that by injecting carriers, you can force this exact topological transition from closed to open. Furthermore, Boyd's group showed that near this transition point, the epsilon near zero region, material exhibit a giant optical nonlinearity. This means that our laser trigger doesn't just nudge the system. It catapults it into this new regime violently and instantaneously. Next slide, please. Viewers confirmed in Nature Photonics that gold nanorods can indeed be switched on and off by femtosecond pulses, and Jacob's work on the broadband Purcell effect proves that once we are in this hyperbolic state, there is no limit on the number of vacuum modes we can couple to. Next slide. The consequence is what we call vacuum breakdown. We move from interacting with a few discrete vacuum modes to interacting with a continuum of high momentum states. The energy density jumps from passive -10 to the 4th to an active -10 to the 8 joules per cubic meter. We have effectively ignited the vacuum. Next slide. Okay, but static density is still not enough. To warp space-time, we need a relativistic gain. We take this localized vacuum breakdown and we rotate it. Next slide, please. Okay, here it should be an animation, but the laser rotates along the track at ultra-relativistic speed. We will see in a moment how we will achieve this. When the source of the vacuum effect moves at this speed, special relativity works in our favor. Next slide, please. The energy momentum tensor components are amplified by the square of the Lorentz factor gamma squared. This means that even a small amount of negative energy, when rotated with a speed approximately equal to c, acts as a massive negative gravitational source. So this is the most important slide. You will see that this negative energy point, the gravity of this negative energy point is incredibly amplified. And quantum energy inequalities does not hold here because the system is not static, it's not isolated, and it's not in free space. So we cannot use quantum energy inequalities. The gravity of this single point is enormously amplified. Next slide, please. Okay, now that we have established physics, we must face the reality of building it. This leads us to part 2, the engineering constraints. Next slide. We have derived a set of strict constraints that must be met for this device to work. We have identified 3 constraints on the metamaterial, nanorod's density, activation time and reset time, 2 constraints on the laser, temporal and spatial Nyquist limits, and a crucial thermal equation to ensure we don't melt the device. Let's analyze them one by one to see if the current technology can meet these constraints. Next slide, please. First, the density. For the metamaterial to support a collective plasmonic state, the nanorods cannot be too sparse. Our calculations show we need a fill factor greater than 28. Current lithography techniques allow us to reach densities over 50%, so the constraint number 1 can be satisfied. Next slide. Next, the timing. This is a critical constraint. To maintain a continuous warp bubble, the material must react instantly. We calculated a required activation time of 1 picosecond, between 1 and 3 picoseconds. Gold nanorods have an electron phonon relaxation time in order of the femtoseconds. This means the material is naturally faster than our requirements. It can switch on and reset fast enough to handle the rotation speed. Constraint number 2 and number 3 are satisfied. Next slide, please. Okay, this is also a constraint about time, about reset time, but as I said, is the constraint number 3, and it can be satisfied. Next slide, please. Okay, now the laser. To simulate a continuous rotation, we must satisfy the Nyquist sampling theorem. We cannot have gaps in the trajectory of the light blade. This dictates a laser repetition rate in the terahertz range. While high, these specs are available in modern commercial pulsed laser system used for industrial cutting. We don't need to invent the laser, we just need to buy the right one. Next slide. This is the equation of the power expenditure, which increases with the laser frequency. The peak power is about 150 kilowatts. Next slide. This is the temperature equation. To avoid the damages to the device, we need a 1% duty cycle, so the lasers cannot be open the whole time, just 1% of the time. Otherwise, we melt the device. Next slide. Now we move to part 3. This is the art of the machine. How do we rotate energy at a light speed without moving parts? This is a big question. Next slide. We use a 4-stage optical chain. The source, an high-power laser, the multiplexer, an optical delay line that boosts the pulse rate to create a continuous stream, and the scanner. The scanner is the key. We use an electro-optic deflector, no mirrors, no motors. It steers light using voltage, achieving the attosecond precision phase controls we discussed. Finally, the projection. An inverse telescope expands the beam, and a 45-degree conical mirror injects it radially into the torus. Result, a blade of light that sweeps the nanorod with a speed approximately equal to c. It's a bit difficult to see, but you must imagine this laser come from above against the center of the torus. The EOD transforms this fixed ray in a little circle. The inverse telescope enlarges the diameter of the circle, and the 45-degree conical mirror injects the circle radially into the torus. So the only limit we have is the frequency, the maximum frequency of the EOD. So it's a limit only about the angular velocity. Increasing the radius of the torus, we can move as close as we want as at the speed of light. Next slide, please. Okay, now we move to part 4. What can we do with this device? Next slide. We see a 3-stage roadmap. Phase 1, the Earth's moment, using the device as a transmitter to generate high-frequency gravitational waves. As we calculated, with a relativistic gain of 10 at the 8, we are well above the detection threshold of current sensor. Then we have the phase 2 midterm repulsive flight. By scaling the effect, we generate a macroscopic repulsive force against Earth gravity. And finally, we have phase 3, the true warp drive. It requires huge scaling the energy density to curve space-time for interstellar travel, but is far above in the future. Next slide. This slide proves the amplitude of the generated gravitational wave increases as gamma squared. This is very important because otherwise gravitational wave cannot be emitted. Usually the physics response at the question, can we emit gravitational wave, is no. But if we use the correct approximation, so we find arbitrary speed, and I underline arbitrary speed, we will find that the amplitude of the gravitational wave scale as gamma squared. So it's possible to emit such waves. Next slide. With a gamma of 10 at the 8, the emitted waves are detectable using these Lee-Baker detectors. The sensitivity of the Lee-Baker detector is entirely theoretical, so we don't have actually a Lee-Baker detector, but in the near future it will be possible to create one, so we can also listen to this gravitational wave. Next slide. This slide underlines that the source rotation frequency must match the detector resonant mode exactly. It's just like a radio. If you emit at a certain frequency, you must listen to that frequency. Next slide. Okay, this is the cost part. Let's talk numbers. The bigger cost is the creation of the metamaterial, because we don't have a procedure to create a metamaterial in a torus. We can create only planar surfaces. So it's a huge voice. Also the conical mirror, it's a huge voice, and the laser also. Next slide. Okay, we estimate a construction timeline of 24 months, involving a multidisciplinary team of optical engineers and nanotech specialists. To summarize, we are moving from passing Casimir to active plasmonic states. We have engineered a metric with the negative energy density. We achieved this with a solid-state design, no moving parts. The physics is sound, the technology is available. I will leave you with this thought. For decades, we asked if space-time could be engineered. Today, the math, the materials tell us that the answer is yes. The question is no longer if, but how fast we can build the first resonator. Thank you for this presentation. I'm open to question, any kind of question, if you have anyone.
Okay, awesome. Giovanni, thank you. Thank you, man. Hey, before anything else, let me see. I'm going to try and bring everybody in here. We got a couple of empty chairs. Guys, put your hands together. Enormous applause for Mr. Giovanni Cambria. Enormous applause. Guys, thank you. Giovanni, thank you. And being the sneaky person that I am, while you were speaking, I downloaded the video presentation and uploaded that in MP4 format. I put that into chat, and so people can see that on the Alt Propulsion channel as well. A couple of folks had asked if you had a paper written for this. I'm not sure if you do or not, but they can always go back and refer to the presentation, and that was really in depth. So it was wonderful.
Yes. In order to explain this, actually, we don't have a detailed mathematical model for the interaction with the laser. So the metamaterial interaction with the laser is not explained by the detailed mathematical model. When we have this model, we will try to publish in a peer review. We have just an order of magnitude and a big picture of how this thing could work. But everything else is set. Once you assume you can decrease the energy density above the usual Casimir effect, everything else is almost set. So we need just this central part to publish our work. After the publication, we can try to, I don't know, create a startup, find a startup accelerator to bring those stuff to reality.
Okay. Okay. Well, that is awesome. Guys, do you have any questions for him? We've got the crew here. We've got Joel. And so Giovanni, you are in, I think you're in Italy, right?
Actually, I'm in Italy. I'm in Messina. Okay. Sorry for this smartphone.
No, that's okay.
My PC didn't work, but yes, I'm in Italy.
So let me thank you for staying up so late. And the reason that came to mind was for Joel as well. Joel, thank you for staying. Joel's in Germany, you're in Italy, and we traditionally go by noon. I see Drew raising his hand. Drew, what's up, man?
Hey, I saw in there a construction estimate, 24 months. What's that based on? I mean, do you have plans or?
Actually, just a rogue estimate. I don't have any plans because first step will be publish this in a peer-reviewed journal. So after this, we can move to the actual stuff. But actually, I don't have any real plan to build this stuff, the device in the present. In the far future, yes.
So if I could ask, in terms of metamaterials, then have you given thought to like the best materials, have you thought about layering or anything like that? I know that area is still really nebulous, right? A lot of paths are converging on this idea of metamaterials, but I think it's still very vague for a lot of folks.
To be really honest about the metamaterial, actually I had only the idea, take a negative energy density point and make it rotate very fast. All other details have been developed using a little intervention by physics freelancer, and also artificial intelligence. So everything else, my idea is just the core idea. Everything else is by physics and by artificial intelligence. I hope that this is the best way. I cannot say otherwise if there is a best metamaterial or something can be done better. I don't know, to be honest.
No, that is totally cool. You know, I'm working on I'm working on a story that touches on the Alcubierre warp drive again. And Miguel Alcubierre did the same thing. He had the core idea. He's like, look, here's the math, here's the idea. This is what may be possible. I don't know exactly how this might be built in the future, right? And that's science. It doesn't move forward all at once.
This is a step more than QBR, because we have an idea about how to build this project. But it's not just pure math. It's an idea about how to build a real project. But the details can be changed anytime. For example, we can conceive variation with a planar surface, not using a torus, using just a laser spot that is called also in literature flying focus, that moves along a flat surface at nearly constant speed. During the acceleration and the deceleration phase, the laser is turned off. So we have just a spot that move at constant speed. You don't emit gravitational wave, you have just the negative energy density, or colloquially the negative mass. This is a possible variation of our device.
Okay, awesome. Jared, go for it.
Yeah, I had a question. Excellent presentation, Giovanni. So at the frequencies and materials that you're talking about very low terahertz, very high gigahertz pulses in titanium dioxide, along with maybe some other possible things there. But as I understand it, and I'm no expert, but as I understand it, when you're dealing at that frequency regime, you can get all sorts of other unintended effects in your materials that could complement your effect or could dampen your effect. Have you looked into the material constraints at the frequencies that you're dealing with?
The only input to my idea are the reset time and the activation time of the nanorods. Since the reset time and the activation time impose this high frequency, it's almost not avoidable to have such a high frequency. Such a high frequency can have other effects that can dampen the Casimir effect. So an important study field, it's born here, because I must really understand well if there are other effects. I think yes, I think they are, that can dampen the Casimir effect. But since activation time and reset time are so small, it's not avoidable this. Otherwise, we must use some other kind of nanorods, or, for example, some of the kind of Casimir effect. I don't know how to avoid this problem.
Interesting.
Also,
so how? Oh, sorry. Go for it. Go for it.
Just one follow-up question for, again, the material constraints you're dealing with at the power densities that you're talking about. Wouldn't that cause ablation of the material?
Yes, will they cause ablation, and in particular, there will be thermal effect. That's why we use a 1% duty cycle. So 99% of the time the laser is switched off, and just 1% of the time the laser is on. This way we can control in a certain way the final temperature. Otherwise, the device will burn. It's impossible to build such a device.
Well, so Giovanni, let me ask what inspired you to do this idea. And the reason is, you know, you approached me and you said, I want to present on this. This is something that I've been working on. That is what APEC is all about, right? Taking people who are focused and passionate and working on these ideas. You are on the theory side of things. Folks like Drew, Jared, you know, Larry, they're on the experimental side of things, right? And like our goal is to try and bring everybody together, you know, and that's like herding cats more often than not, but you know, but like it works overall. What was your inspiration for this?
I always ask it to myself, is it possible to engineer negative energy density? Because theoretical physics say no, we cannot have negative energy density. At the Italian facility, ENFN, we are So they are creating an experiment in order to measure the decrease of weight related to Casimir effect. So we just two pair of plates. They want to measure the decrease of weight. I just wondered if this decrease in weight can be amplified, so the measure become easier, and I spotted this possibility. So if you amplify negative energy density and tangential pressure together, if the sum is negative, this sum is amplified by a gamma factor, a gamma squared factor, 2 gamma squared. So it's an important thing to investigate on, because it's an amplification enormous. With a gamma of 10 at the 8, you have an amplification of 10 at the 16. So it's a truly remarkable possibility. It's important to understand it fully.
So for like future engineering, and I know that you don't have a full plan laid out for this, right? But I'm sure you've given some thought to that. Is this something like Sonny White is working with basically like almost nanomaterials, micromaterials, right? For the Casimir effect, for energy generation. And he is pushing towards like semiconductor manufacturing techniques for that. I think that's something that Dr. Garrett Modell is also looking at. Are you visualizing something like that? Like being able to maybe even mass produce something based on this?
After the prototype, yes, we hope to mass produce this kind of stuff, but it's too early to speak about this. Actually, I've seen that in literature, in physics, they are moving to only positive energy density warp drives. And I think they are missing a point, because negative energy density, and this is my most important point, is not impossible. It can be conceived, it can be bring to reality. So it's important to investigate first this negative energy point at our maximum capability. Then we should move to positive energy density. I think it's not impossible as it seems.
Yeah, yeah. Well, and then one thing that comes to mind, and I hope that I'm not misstating this, I probably am, but in addition to true negative energy density compared to the background vacuum state, right? So you have the vacuum of space and you're going negative below that, right? And like that happens when they create antimatter. It's, you know, you're applying positive energy and it's kicking out an antiparticle, right? So you've got like a negative energy hole remaining there. There's also this idea of negative energy above a ground state. And that for me was really intriguing. The first time I read about that, Dr. Eric Davis wrote a paper, I think it was 2006 or 2007. And again, I hope I'm not saying this incorrectly. He had talked about spinning a field. And if I understood it correctly, the centrifugal force was kind of the equivalent of negative energy density. He was saying, if you take the field and spin it, you can satisfy these equations because the spin is basically forcing things out. You're creating a negative energy space from that, right? Now, obviously, this is above ground state because you're putting energy into the system, but you still have a difference between two energies and you're able to create negative energy state.
To be honest, I don't know about this particular paper you have mentioned, but I want to comment a little bit about acceleration. Actually, in our device, there is no acceleration at all. Yes, the negative point spin in circle, but is an excitation of a background. So there is no physical body that accelerate and that must sustain this acceleration. For so large speed, the acceleration will be enormous and will disintegrate any physical body. This is not a physical body, it's just an excitation of a fixed background. So we don't have an acceleration problem in our device.
Okay, that makes sense. Yeah, well, Larry, go for it, sir.
Back about 35 years ago, I was working on a device that worked at high vacuum, and I call it a casting process. It sounds to me like what you're doing is it Giovanni, that you could actually use your system in a casting process in a enclosed environment where you could create real high purity compounds out of it. Have you thought about maybe using it like that?
No, actually, I haven't thought this, but we can speak about this in the future or after the conference if you want.
Yeah.
Yeah, amazing, amazing. Guys, any other questions for Giovanni? Joel, go for it.
So first of all, thanks for the presentation. I'm still trying to really understand what you're trying to do. And so if I've got it right, you're actually trying to do something like the Hertz experiment for the EM field. So you want to prove basically that space-time engineering is doable, and you want to show a way to actually do it, which
Yes,
would be
exactly.
amazing. Definitely, it would be amazing if you could establish that as a fact, because it would, I think it would gather a lot of attention and really prove that space-time engineering is something that we can do. And we're trying to do it for some time now, right? So also the idea to then go beyond and have some kind of field drive development from that point is very interesting. But I really applaud you for the idea. I think the experiment looks very, very good. But I also the question of Jared, if the material is gonna hold and if everything is gonna, like, the theory looks nice, but I also fear that if you try to actually do it, that there are gonna be problems. And also, I'm still trying to understand if where exactly is the negative mass or energy coming from? Like in the is it in the stress? Is it really negative mass? Where is it coming from exactly?
Okay, I will explain a bit better where the negative energy density is coming from. So you have a torus with a little negative energy density and a little spot, a laser spot on the torus with a negative energy density more negative than the rest of the torus, okay? So you have this point of more negative energy density and you spin it along the toroidal track. And as you spin it, the stress tensor, the trace of the stress tensor undergoes a nonlinear amplification. So you have a gamma squared, like in particle accelerator. The original negative energy density comes from the Casimir effect on the metamaterial. So on the Casimir effect
because you have a small gap already engineered in the metamaterial.
Yes,
But
yes.
Is it an engineered property or is it just a property of the material you're using?
The basic state is negative already in the metamaterial, so there is no need to do anything. It's when you create the metamaterial with these tiny nanorods, this parallel stack of nanorods, you already have a negative energy density. When you hit them with the laser, this energy density become more negative, so in modulus it's become greater. So you have a spot of negative energy density that moves. That's the whole thing. It's about moving this spot.
Okay, thank you.
Yeah, wonderful, wonderful. Giovanni, I'm so pleased. I'm so pleased that you were able to present today. I'm really excited. Guys, do you have any more questions for Giovanni? Yeah, Jared, go for it, sir.
So regarding the laser and how it is rotating around the torus, what physical mechanism could you use to get that laser beam to spin around as fast as is necessary? Because you were saying like near relativistic speeds required for that, angle of rotation.
Yes, yes.
How do you spin a mirror or something to get the beam to spin around fast?
Okay. There are no motors and no physical parts that moves. The laser came from above the torus. It's pointing against the center of the torus. Then the laser traversed the EOD, electro-optic deflector. And then this laser, that is a point that go against the torus, become a little circle with a very high rotational speed, very high angular speed. This little circle traverses the inverse telescope and it's transformed in a large circumference. So the rotational speed remains the same, but the circumference is larger. Then this high diameter circle hit the conical mirror, and you should see it by above the conical mirror and is injected radially against the torus, because the conical mirror is at the center of the torus. Maybe it's missing in the slide, it's not so clear, but the conical mirror is exactly at the center of the torus with his arrow pointing upward. So when you hit them, you are injected against the torus. So the only limit here is the angular speed of the EOD. The angular speed of the EOD can be very, very high. Furthermore, you can also increase the radius and you can achieve a flying focus speed very close to the speed of light.
So I have maybe another question. So when you say mu goes below 0, so which full T mu nu do you use in the active state? Do you include the medium and the pump, or just the vacuum part? Because look, what I'm thinking about is, so you have basically a material in which a Casimir effect is occurring, and then you're pumping a laser which makes the material undergo a topological transition, which in some kind gives this passive Casimir effect a boost in strength. And then you
Exactly.
say, you see, I have a much bigger negative energy. But is this just locally? So do you have really a negative T mu nu in the whole area, or just on a very small spot, which gets
Just on a very small spot, but this very small spot moves. So you have just this very small spot with decreased negative energy density, and you move it at a very high speed.
Okay, I see. And especially because you move it, you think that you can actually generate GR waves and measure them, right?
Exactly. You could generate gravitational waves and measure them, but my primary focus is to measure the decreasing weight. This is the primary focus because it's the simpler thing you can measure. A decreasing weight, it's very important to, and if you make the weight 0, of course, will be super interesting, but also a little decreasing weight will be interesting for all the scientific community.
Of course, yes. Yeah, very interesting. And you've had a cost estimate in the end. Do you have an actual plan to get that money, to get the funding, or?
After the peer review phase, I will create a startup. I don't know. I will try to find a founder because 1 million it's a big cost, and if you must pay also the specialist, it easily increases to 2 million and more. So a founder is needed.
Okay, yeah, that's a usual problem, but I really hope that you will get the money and can do the experiment. It looks very promising.
Thank you.
Wonderful. Well, guys, yeah, so we got about 10 minutes left until George comes on. George is not here yet. Curtis is here hiding in the backstage, but now he's not hiding. There's
Hey there.
Should I turn it off? Curtis is
No, it's okay. I'm here.
Okay. He's suiting up. He's suiting
Yep.
up. Yeah, Giovanni, I'm really excited, man. I'm so pumped up that you were able to present today. We're like limping back into the new year, right? Like that's been my experience. And just in general terms, this is just me, but like every January, it like takes off like a rocket, like right at the beginning. And I'm like, what's going on? Then I'm like, oh yeah, it's January. Everything's starting to move forward again.
Perfect.
Yeah, thank you. Lee.
Are you listening to it? No, it's too hot.
I'll just sit right there. All right. Thank you.
Crackers. Is it on?
Yeah, it's on.
I can't even hear it.
Okay.
Marlene. You hear it?
Yeah, I can get it.
Yeah, so we've got, I think we probably have about 8
Not
minutes
good.
until George is due to present. Guys, do you want to give us any rundowns? You guys want to do open discussion or chat or anything like that? A couple of minutes?
I had another question for Giovanni.
Go for it. Yeah, go for it. And I'm actually going to use the restroom really quick, so I'll be right back.
So regarding the materials that you're talking about, have you considered any alternate materials than what you presented?
Allora, the first time I thought about this, we considered a different scenario with the metamaterial with a different activation state and reset state. But the transition, the topological transition, was ignited by heat release. So the transition time, the activation time, and the reset time were much higher. This could lead to a completely different setup for the whole stuff. So it's not my first attempt; it's the second attempt. The problem with heat release is that it will you must make the stuff more. So it's not easy to dissipate the heat. It's very difficult to dissipate all the heat you need if you use it in order to activate the topological transition. If you use photoelectric effect like us, then it's much easier to achieve, but also require a terahertz range laser that melt the device unless you use a 1% duty cycle.
Also, since we're talking about nanorod metamaterials, does that mean that you're actually dealing with negative effective energy rather than actual negative energy?
The 0 point is the vacuum point, the vacuum energy. So it's not effective, it's actual negative energy, because it's like normal Casimir effect. If you see it, when two nanorods are close together, you have the simple Casimir effect. And this is a low efficiency Casimir effect because gold is transparent to some electromagnetic waves. If you hit the gold with the nanorods, you change the contour conditions and the gold become less transparent to electromagnetic EM waves. So the Casimir effect improves its efficiency. And so become a more efficient Casimir effect, and so the energy density is lower. The 0 is the ground state, so the vacuum state.
So
I didn't actually hear any dimensions in the thing. So let's say you build a prototype. How big of a warp bubble can it make? Are we talking about something the size of a proton, something the size of a flea, a car?
Oh.
How big is this thing?
Okay, I will explain. The dimension of the torus is 60 centimeter. The effect, the decrease in weight is very small with a gamma of 10 at the 8. The decrease in weight is about 9 grams. So it's very small, but it increases as gamma squared. So with a bigger gamma, you have a bigger decrease in weight. With just
got
a
nothing
little
out of that.
torus.
How big is this thing?
How big? You mean the rotor, the circumference?
Sure.
The circumference is 60 centimeter diameter.
Oh, 60 centimeters.
Yes,
60
very
centimeters.
little.
About
It's
20
something you can host in your table, in your laboratory table.
60 centimeters.
Because that,
Oh. Okay.
that's a little 2 inches.
That's big enough to put a microwave oven inside of.
Yeah.
All right, thanks.
Thank you.
Yeah, so we're
maybe
rolling.
to
We are rolling.
reframe.
It looks like George is not quite here yet. He may.
He said, I put the message in the private chat in the YouTube comments. He said he's here and he doesn't know how to.
Oh, okay. I see it. George. So, George, since you are listening, I'm going to email you the StreamYard link. Okay. And as soon as I find it, here we go. Okay.
So maybe
I'm gonna...
to reframe my question one more time, Giovanni. In your general relativity source integral, which specific quantity should we think of as the engineered source term? The renormalized T mu or the EM field or the effective T mu for the combined system?
I think it's the effective one. Usually, you have negative energy density and azimuthal pressure in the moving framework, and you have negative energy density and tangential pressure in the lab. So the relation between the two is negative energy density plus tangential pressure in the moving reference frame by gamma squared. It's equal to the other one. It's the okay.
Mm-hmm. Yeah, that's okay. That makes it a little bit more clear to me, because I think that's a very interesting part and point that not everybody, not even every physicist, really realizes. And I think this is what we have to use for real space-time engineering. So T mu is not just energy density, right? It is energy density, it is pressure, it is stress, and momentum flow. And so
yes,
if you, for example, get a negative pressure, which is big enough to make the whole term negative, then you're already there. So yeah, very good.
Yes, it's not only negative energy density, it's also tangential pressure. And in this particular system, tangential pressure is equal to negative energy density. So you have 2 times negative energy density. Because the orthogonal pressure, the pressure along Z, it's 0, because the stack, it's quite easy to see. You have a stack of nanorods, and the void above a nanorod it's equal to the void below the nanorod. So the pressure along Z is 0. All the energy density goes in the tangential direction. I don't know if you understand.
Yeah, that makes sense. Yes. Yes.
Oops. Okay. And so George is here. George, it is not letting us display your. Let me see. It says you'll need to connect your mic cam before you can add them to the stream. So if you go down to the settings, so StreamYard is a little bit different than Zoom. It's a little bit different than Riverside. I'm not sure which one we did when we did our podcast interview. But if you go down to the bottom of your web browser window, there should be a little mic and a little up arrow, and it'll let you select which one you want to use. And again, Google Chrome is the best tool. That's the best browser to use for this. And the reason is all of these, Riverside and all of those, they leverage, okay, there's, oh, okay, George disappeared. He might be coming back in. Yeah, all of these leverage basically built-in functionality that Google put for Google Meet. And so it's both a blessing and a curse. It locks people into Chrome, which I suppose is what they want.
Another little thing I want to add, since time is almost over. The laser also has a positive energy density, also a tangential pressure positive, but the Casimir effect is way higher as order of magnitude than the laser. So the total sum is still negative. A possible objection is, but the laser has a positive energy density, you are not considering it. We are considering it. In the slides, it's clearly stated that the negative energy density of the Casimir effect is in modulus higher than the positive energy density of the laser.
Wonderful, wonderful. Okay, and he is, let me see, he is trying to join. He might be having to configure his stuff, so we'll give him a sec if it's okay. And then I do have George's presentation also. I've got that queued up. He sent that over a little while ago, the 4 archetypes of catalytic fusion. Hopefully he has not made a bunch of updates or changes, but I have been digging through my inbox, and this is the last version of it that I have. So
Could you actually, I think the weight measurement might be the easiest one to go for, but could you actually measure somehow if this point actually carries real momentum flux? That would be very interesting.
Yes, I think so, but to start, I think the best thing to do is to measure a little weight decrease. Decrease in weight. Then we will move to gravitational waves, and then we will move also to kind of momentum flux. In particular, if the weight become completely negative because you cannot limit yourself to a 0 weight, you can also move to negative weight. I think this device will lift up as for the biometric gravity model, because I use the biometric gravity model. I think this device, if the weight is completely negative, will move against the gravitational force. So it's important for aerospace and defense industry. Work in aerospace and defense from 2012, so for almost 14 years, I know how is important vertical takeoff. So it could be an interesting application.
okay, and George is back again. George is not letting you. Would you want to try? Let me see. It's not letting you connect with that. So we may. So it may be a permissions issue. Okay, so what I'm going to do is send you, let me see. It has a thing that says my mic does not work. Hang on. There's Orestis. Okay. Orestis, welcome.
Hey,
we're giving George just a moment here, and what I'm going to do is email George. Yes, okay. I'm going to email him here the link for StreamYard support. Basically, you have to give the web browser permissions to use your mic and camera.
Are you saying that to me, or can you actually hear me?
Yes, I can hear you. Yeah, Orestis,
Okay.
you are fine, sir. Yeah, I'm trying to give George another moment. So George Egely is scheduled to present now, but if we can't make it work, I don't want to hold things up too much. We could go to you if you're okay with that.
Sure.
Okay. Orestis, do you want to upload your presentation? Do you have the PDF that you can upload?
Sure, I do. It is a summary of what I am going to talk about, basically. It's not much.
Yeah,
Because,
that works.
yeah, sure.
Okay, well, why don't you do that then?
I think that's it.
Yeah, and it'll take just a second to display. And I just don't want to hold things up. It's
Right.
StreamYard is a little bit different, but the multicasting capability makes it really, really handy. So
That should be it.
there we go. Okay,
Yeah.
I'm going to add that. Okay.
All right.
And we don't have to put that up if you don't want. Those are mostly just notes, but that's fine.
Yes. Yes, actually.
Okay, here, I'll take those down. So why don't I do this then? Why don't, if it's okay, if George is able to come back, or if he's able to work on it for about an hour or so, let's go to you for an hour, and then we will come back to George. And George, again, my apologies for the StreamYard bugs. It works most of the time for most people, but computers in general are not always fun. So what I will do is I'm going to take everybody else out of the studio for now. Okay. And Orestis, thank you so much. So you are, and actually you had issues in December. So it's computers,
Yeah.
man. So you have been doing implant analysis, like detailed UAP ET implant analysis. So if it's okay, I will just spotlight you for the audience. I'll take myself out and I will be here. Let me know if you need to put anything up on the screen or anything like that.
Sure, sure. Thank you, everyone, for joining. This is a wonderful opportunity and that I've been looking forward to. Like Tim said, of course, we had some issues, from real life last time. But now, God willing, we should be left uninterrupted. So, tonight, I will present to you the ongoing investigation, scientific investigation that I have undertaken on a number of allegedly anomalous samples that came from different sources, different cases, none of which are famous or widely known to the community. So that's a first step. Basically, they are objects recovered from out in the desert or from inside a human's body. And in that particular one is one of them. It was removed, no blood at all. It started breaking down, textbook, basically, of what Dr. Lear wrote about. Fits the description of an alien implant, that's for sure. But descriptions alone will not make it. So I wanted to see exactly how anomalous they are. So I subjected them to a number of different techniques, different instruments. We wanted to check the elemental composition. We wanted to check the crystal structure, even the fine details down to the micro nanoscale would be important. We're looking at complete unknowns here, so we don't have anything to compare them to. So best we can do is start slow, start from the surface, and gradually work our way down using the available data, the scientific literature, and just anything that we can find, basically. So that was the goal. The goal was to see if my samples were anomalous or mundane or terrestrial. That's the goal here. You know, we can engineer all sorts of things today. We can etch details at the nanoscale with lasers, but it shouldn't be so. For a lot of those techniques, technically we can accomplish them today, but it would be so much expensive that it would not be worth it. So, sparing all the rest of the details, 3 different samples have been recovered. One of them was from an unknown object found out in the desert somewhere, and it was just there. No beings. There were no beings. There were, you know, no reports of anything going missing or going down. It was just found there one day, and parts of it, you know, have made it to people's homes and started causing all sorts of trouble. Electrical appliances would go out. People would start to faint around them. It was kind of difficult. So I requested that some of those objects be sent to me for analysis, and I took them to 2 different labs in Athens. One of them is the Center for Scientific Research, Demokritos, and the other is the Eurofins Athens Analytical Laboratory, because they have some machines that the other one doesn't. So a scanning electron microscope with the accompanying elemental analysis X-ray test was the first step. We found that the majority elements were always 2. You always have 2 majority elements and a number of, you know, minority or trace elements. The majority elements were titanium, iron, chromium, and copper, which was odd. We don't usually see copper in, you know, as a majority element in a lot of UFO samples. So we checked, and I have already done a lot of presentations with pictures showing the details and the elemental compositions of some of those samples. But tonight, I will tell you about the isotope tests that we did. The isotope test is what we do to certify whether a meteorite is a meteorite, for example, if something occurred from Earth or from somewhere else, or if it was engineered. So those are the 3 possibilities. It's either natural terrestrial, natural extraterrestrial, or engineered. And so you don't know where it comes from if it's engineered, you know. So basically the isotope is the number of neutrons in an atom. If you take a pile of dirt and you extract all the copper from your dirt, about, figuratively speaking, about half of the copper will be of one isotope and the other half will be the second isotope. Copper has 2 isotopes. That's what isotopes are. Every element occurs in isotopes. And those are the stable ones. The radioactive ones are a whole different story. So on Earth, the ratio between the isotopes of a different element are fixed, more or less. But for the most part, they are very much fixed and known. So you can tell if your object, you know, comes from Earth or from space. And that's how we tell meteorites from Earth rocks. So in our tests, the first method we used, because there were 2 methods, the first method came with all sorts of problems. The first method, I just subjected the sample and told them to run tests for all the isotopes of all the elements that they could find, and, you know, hoping that I would get the isotope ratios. And of course, it doesn't work that way. And I found out the hard way, because there are all sorts of noises in the system. One problem is the mass overlap. So you will have isotopes from different elements having approximately the same mass. So the number of protons is what differentiates copper from chromium, from titanium. That's all the difference in the number of protons. But the neutrons can be the same. So there is an isotope called chromium-50. There is another isotope called titanium-50. They're from different elements, but they have the same number of neutrons, 50. So they are mass 50. Let's call them mass 50. And that's a problem. ICP-MS, the test that we did, does not have the resolution to tell the difference. So if you have 10 units, you don't know how many of those units are titanium and how many of them are chromium. Then there are other problems, because during the machine's operation, you have all sorts of gases interacting with the sample and with one another. And sometimes those gases can stick. Atoms from different gases can stick, and the combined can be attracted to another combination, and suddenly you have an amalgamation of different gaseous atoms large enough to register as an atom of your sample. So that can also get mixed up in the data. So given these two, it is generally a bad idea to go in with so many elements, so many isotopes that overlap. Mass 50, mass 30, mass 23, all these problems. But we did the test nonetheless, and the results came back. They were impressive. I was like, hey, if that's real, these things are off the charts. Could be real, but they were, it was too risky to just rely on those results. And that's the problem. That's a problem for a lot of research nowadays, is that one test is done, numbers are presented, and no data. And the data, the accompanying data, is more important than the numbers presented, because the reports, the lab reports, the tune reports, the calibration of the instrument, all these things have to be taken into account in order to assert the accuracy of your test. We learned this along the way, and we did the test again. We did it a second time. And this time, we only tested the non-overlapping isotopes. So chromium-50, titanium-50, we did not test those. All other isotopes that do not overlap were tested, and there is the second run, the second method came back with its own results. And then there was another problem, of course. They say that for every problem exists a solution, but it goes both ways. For every solution, there is also a problem. And the problem for the second solution is that now, since we have excluded some isotopes from, let's say, titanium, now we only get the ratios of isotopes one to another. But if we do not know all of the isotopes, then those isotopes that are missing take an X amount of the 100% that you don't know about. So you cannot accurately predict the number. You cannot calculate how much of each different isotope is in your sample. And that kind of defeats the point, right? But there is another solution. See, all right, we know a few of the isotopes. On Earth, we know the numbers. We know the ratios for Earth, right? So the ratio between two isotopes, one to another, is known, is a known factor, is a known thing. So if titanium, for example, has 5 isotopes, and we exclude those 2 of those 5, we cannot tell the exact number of the other 3, but we should be able to compare the ratio between one isotope to the other and the other to the third, 2 isotopes at a time. With this method, even though we cannot tell the number, we can finally know if there is a large difference, a big difference between the ratios of 2 isotopes, one to another, compared to those ratios, 2 isotopes, one to another, of Earth. And that is called the delta notation, basically. You take one isotope that is lighter and another isotope that is heavier, and there are some equations that you do, and mathematically you get a number, and that's the delta notation difference, basically, the ratio, one isotope to another. And that kind of solves most of the problems, but now we also had to deal with mass bias and the what I said before, the polyatomic interference, where all these other atoms stick together and they register as sample atoms, even though they're not. To get rid of that issue, we had to use the MS-MS technique, the triple quadruple method of the ICP-MS, which is better than the single quadruple. Basically, you have 3 processing units, and their data is fed to the 2-step process of MS-MS, MS/MS. And there, for this whole package, basically, the machine asks, it's like asking, like, are you titanium? The thing that is in front of us says, yes, I am titanium. The machine says, all right, if you really are titanium, you will survive if I shoot you with some gas rays. And then gas is introduced into this thing that claims to be titanium. And if it breaks down, if it breaks apart, it was not titanium. It was an amalgamation. But if it stays whole, it was titanium. And the same is repeated for basically everything, to the point that the noise in the system and the window of error, the uncertainty, is reduced down to 0.5%. So we have a very good, standard. Our results will vary by 0.5% at most. This is very important. With all those in mind, we get a purified result that can be, you can compare it to a box full of fruits. So if you have a factory, let's say that we have a factory, and it produces, it processes fruits. So you have 3 kinds of fruits inside your box. You have apples, you have oranges, and you have bananas. Now, for that factory, the ratio between the fruits is the same. It's 1/3 apples, 1/3 bananas, 1/3 oranges. So it's 1/3 of each. Now, if you find the box and you have a lot of different fruits in there, you don't have the time to count all of them, or you just can't. But what you can do is gather each different fruit in piles and then see if the total volume, right, is the same amongst the different fruits. And if it's not, by a lot, then you just found yourself a box that either came from a different factory, or someone opened the box, added or subtracted fruits, and engineered the contents. So if the Earth is this factory, right, and if our samples are those boxes, then we don't need to know the exact number. We can tell if the sample was tampered with simply by looking the volumes, so to speak, the delta notations. If we find overgrown delta notations well beyond the limits of statistical error, then we can reliably assert that the sample is not just any natural, mundane, earthly rock or metal of something that we made here. So we did this, and the results came back very promising. Most of the isotopes were actually within, the window of error. So a lot of the isotopes were, even though they were off the charts by a little bit, noise could theoretically drag them back into the terrestrial range. But that works both ways. The terrestrial, the isotopes that are already found to be in terrestrial ranges could have been brought there by noise. So, ICP-MS does not have the required resolution to tell the subtle differences in those isotopes. But in some other isotopes, which were found in all three of those samples, the delta notations were huge. Like in one of them, the delta was more than 500 mil. It's calculated, it's expressed in mil, not percent, but per mil. So one delta in one sample was more than 500 of that. The other was 200. And for the third sample, the one with a lot of copper, the delta placed it just outside the worst case scenario for an earthly isotope, meaning that even if all the errors and all the uncertainties are maxed out and applied in favor of a terrestrial origin, even then, that sample was a little bit outside. And by a little, I mean 5 times more than the maximum that you would expect to find in a worst case scenario, applying the worst, the worst possible errors. If you factor in the correction mechanisms of the instrument, the calibration, which was basically perfect. I have the report, but it's pages upon pages of numbers and abbreviations and numbers next to abbreviations. There is just no time to go through it all. And it would kind of defeat the point. The point is that the machine was running perfect. We used 2 methods, and the same anomalies showed up in both methods. Both in the method with all the isotopes and in the method with only the non-overlapping isotopes, we had the same observables. So we have the same pattern. It was not a result of interference. It was not a result of mass overlap, whatever we saw in the first method. So suddenly, the first method, which I thought was faulty, turned out to be a second witness to the same observable. So that's how we know that the samples are anomalous, even though we do not know the exact numbers of the isotopic abundances for each isotope. We don't need that, because we can tell simply by looking at the ratios between 2 isotopes at a time that some of them are so far removed from those of Earth that you cannot find it here. Now, on Earth, natural processes in the ground or accelerated by some bacteria sometimes, they can alter the ratios by a little bit, the isotopic ratios by a little bit, but by a very small amount. It's like 0.005% for copper, for example, a very small amount. Or long-term bombardment by cosmic rays, even more. But the deltas that we found in our samples exceed even those, which is very important, because now it is not earthly natural, and it is not even meteoric. It's not even meteoric. So whatever happened to that sample, someone manipulated it, someone changed it. The evidence so far points to them being engineered. And one has to wonder if they could possibly be engineered on Earth. The answer is yes for today, but not for the time frame in which they were discovered. These objects were found some 50 years ago, in the 60s. There was no terrestrial facility that could achieve that level of isotopic enrichment at that time. Not more than 500% of silicon, for example, in one of the samples. So whoever engineered them, was using technology and knowledge, that was more than 20 years ahead into the future. So That does not prove that it's alien, no, but it does prove that it is exotic and that we couldn't make it here on Earth, at least, not with our technology at the time. So you have to wonder now, if a Beta-2 bomber, stealth bomber, crashes right now in my backyard, the special forces will flood the whole neighborhood, if not the city. They will not just leave it there for Orestis. Someone will come to pick it up because it is valuable. It is expensive to make. It has a lot of technologies, that enemies could benefit from them, all sorts of things. So why would someone leave such expensive, so advanced, so secretive, if you will, craft to just rot, to collect dust out in the desert or in the woods where another one was found? And don't even get me started about the one in the human body. So the point is this: even if they were somehow engineered on Earth, they would be too expensive to just leave them out there. Nobody does that. The only kind of person who just leaves things, out in the sun is someone who doesn't really care about them because they can mass produce them. If you can mass produce them, you can, 3D print them, maybe. Maybe you're so far advanced that they are basic toys for you and you don't give, you don't care so much about them. Which strengthens the case, basically. And really, if they were natural, you would expect all of the isotopes to vary by some crazy degree or by none at all. The fact that only a few isotopes spike in their delta, they are very far removed from expectations, while the others remain kind of near the expected terrestrial ranges, that is even more evidence that they are engineered, that something happened to them. Someone touched these things and changed them. So that's where we are right now. The research is ongoing. We still have to do these more expensive tests to go down into those subtle differences into the other isotopes to see if they also are different, because if they too are different, then we can reliably talk about an extraterrestrial origin. So far, the evidence that as it stands right now points to engineering somewhere, which was probably not Earth, but that's not definitely sure yet. That's where we are. I will be happy to answer any of your questions if you have any.
Orestis, awesome. Thank you, man. Thank you. That was totally cool update, man. Let me bring the guys who have their cameras on. There we go. Not everybody does. Let's put our hands together and give Mr. Orestis Lazanakis an enormous applause. Orestis, thank you, man. Hey, do you guys have any questions? Jared might.
Yeah, Orestis, as always, amazing updates. I love it.
Oh, and there's Joel. Let me put Joel in too. Okay.
Yeah, I was curious. So as far as how difficult it would be to try to recreate even a part of this, have you gone through any steps trying to see what we could do to try to make any component of this? Because it seems like in the process of doing that, that's a good way to try to figure out what the heck is this thing supposed to do, right? Is by figuring out just, can I even make one component?
So that's a tricky question. First of all, you would have to get a few millions, because these things were large. They were not just the samples that I received, though those came from the whole objects, which weigh several kilograms, tens of kilograms. So engineering them here on Earth, yeah, it's possible now, not then, not back when they were discovered. But if we were to even start thinking about replicating something like that, it would first of all cost, an astronomical amount. Then, so this is anecdotal. Now, okay, we talked about all the hard evidence, but since you asked this wonderful question, I have observed some behaviors in those samples that I just cannot explain. Some of them, pieces of them, would respond differently to magnetic fields, for example. I would have this one piece, move it around with a magnet, and it would be very weakly attracted to magnets, meaning it doesn't have a lot of metallics in it. But the surrounding metallic pieces would gather around it, form a ring around it, and then after a certain point, after enough shards basically were gathered around this one piece, the piece would shoot straight up and then straight down, not a free fall, straight up, straight down. I only observed that one time, and I was shocked. Didn't try to do it ever again. I still have that piece, and I would love to work with someone who can look into it more. But I don't want to touch it because I'm too much afraid that I may short circuit something, because a few seconds after it fell down, it separated in two with a line that we can see in the scanning electron microscope, a very fine line. Like, it was strange, man. So I'm not a material scientist. I would love if someone would come along and say, hey, I know what this is, like, but so far I'm not sure. I just don't know if we can. We definitely could not back then. Yeah, that's for sure.
That behavior sounds a lot like the Hutchinson effect. You get like a random levitation event combined with a separating or a splitting of the material. I don't know if it is related. It's just those effects combined together like that do sound somewhat similar to some of the Hutchinson stuff.
Yeah, or something like a non-linear interaction with magnetic fields, like metamaterials. I don't know. Yeah.
Yeah.
Hey,
You're
Larry.
saying the pieces are you're talking about the pieces all being together in one piece, and then the mild magnetic field would and these, I guess I take it that these other pieces are separate, and you push them toward the center, and then they just go up, shoot straight up.
Yes. So I should clarify that particular piece was kind of a dark brown. To the naked eye, it looks black, but under the microscope, it's really dark brown. And it doesn't look metallic, even though it has some calcium and other metals in it. Around it were metallic shards, small pieces, basically dust that had come from the cutting of the sample. I even keep the dust, of course. Nothing goes wasted. And those metallic shards would gather around this, weakly ferromagnetic material. And since most of them, the majority were basically iron. Iron starts acting like magnets. So you have more magnets, appearing around it. So they increase the magnetic field, I suppose. And after a certain amount of shards were gathered around it, then that separate piece shot up, shot down, stayed there. And after a few seconds, it split in two. Yeah,
Well,
like
So it didn't split on impact, but just after some seconds, then it split. Okay.
Yes, and many seconds. I don't know how many, but yeah, many. Because I remember, because I handled it very correctly, very carefully. Like I was like, oh my God, this is important. Let's just put it to the side, not lose it. And when I checked again, it had split in two.
I just wanted to say that when a magnet breaks in two, sometimes the particles in it will resist because they become magnetized. And I guess when they break, they split. I was thinking of something maybe similar to that kind of an effect.
Yeah, yeah, maybe. I
I
don't know. I don't know. And that's just one. There were others, other ones too. Anyone else? Okay. So another one, it was green. It was a fairly large piece. It was green. And when I took that to the scanning electron microscope step, we zoomed in, and I remember it was like a leaf. It was like, have you ever seen a leaf, magnified? It has this network of things, of lines. It's like a spider web, and that's what it looked like. And after we zoomed in again and the image refreshed, that network had begun to burn down, to burn up. It was starting to crumple. It was starting to break down. I don't know. Maybe it was because of the electrons of the scanning electron microscope. But anyway, I just grabbed my phone, took pictures immediately. Didn't make it. You cannot see the network anymore, but it's there. You can see the aftermath basically. And like the other sample, I just left it alone. Still have it. Haven't touched it ever since, because if that is a working component, if it's circuitry, I don't want to mess around with it. So that's where we are right now.
Awesome. Orestis, I dropped in the chat there for you. I found metallurgical microscopes for very cheap from India, and I was able to combine a 4K camera with it as well. So for like $500, which, for a metallurgical microscope isn't bad. Plus you're able to capture right onto your computer with 4K camera. Not a bad thing if you happen to get samples and you want to just pop it under the microscope and be able to, make the slight adjustments, because it has 2-stage motion on there as well. And since the metallurgical, you got the light coming from above and reflecting off of the thing. Might be worth looking into.
It is, because that will save us a lot of time from the scanning electron microscope step. Because when we take a very small piece to the lab, we don't know what we're looking at, so we start looking around for details, and maybe the details are on the other side, and now you have to switch it over. And yeah, but with a good optical microscope style thing, that would save us a lot of time. Thank you, Jared.
Yes, and the scanning microscopes, like you were saying, yeah, they damage the sample, right? If you got something really small and it's kind of in a dark spot, you got to really, pump the beam on that. It starts burning the material, which, sucks when it's one-of-a-kind material.
Exactly. And you don't know what it is. Like, have I just destroyed something important? Oh my God. Yeah. Been there.
But yeah, the metallurgical microscope we got over at Mark's place at Falcon Space, I think we paid $2,500 or $3,000 for that one. And it's a bigger one with a lot fancier stuff going on, right? It's better than the one I'm talking about that's sitting on my bench right there. But for $500 to have a 2000X, a decent 2000X metallurgical microscope, yeah, highly recommend.
Yeah, it's something that's great for the first stages, right before the first X-rays, maybe, because the X-rays are telling us the elements, the elemental composition of the sample. Yeah, because we need to know that. Because exactly, see, the samples that tend to be burned the most are the ones that don't have too much metal in them, like organic or insulating materials. They come with all sorts of problems because they create interferences with the ion beam, and you cannot get high resolution pictures unless you really push those electrons. And yeah, it's a problem. A good metallurgical microscope would just help us a lot in here. Yeah. Right.
Yeah. Well, Orestis, thank you, man. Thank you. Yeah. I mean, the work that you guys are doing in terms of samples, I think it is so important and it is so overdue, you know? And one of the things that surprised me, just like hanging out with Jared, you know, and other folks who've looked at the arts part stuff, is like UAP samples are like almost coming out of the woodwork now. Like they're actually all over the place. Where people like email in, they're like, "Yeah, I know somebody who has some. Yeah, I have some." You know, and then then the next challenge is, okay, I'm guessing most of those aren't legit, right? Like, I mean, there are rumors that like the US government dumps trash at like, you know, crash sites to throw people off, you know? So maybe you'll get lots of like, you know, aluminum shards and stuff like that, but it's still like there's so much out there that is waiting to be analyzed. I think it's really important, you know? And so like folks like you to be doing the science and categorizing it and all that, that's really critical.
Yeah, thank you. That's very true. And the rumors, you know, it's not only the US government. Apparently the Greek government does the same, because in the 1990 there was a sort of, not a crash, a forced landing, if you will, of a UFO. And you know, people saw these things. They saw, you know, little children coming out of it, you know, doing something to the craft and then taking off with the other lights that came down. And you know, next day the Air Force, they presented a report, you know, with alleged material recovered from the landing site. And it was, you know, it was obviously copper tubes and cables, human technology. Some of them even had some letters etched to them. And then, therefore, they concluded that it is a satellite. Now, which satellite has crew, it can be piloted, it can, you know, land and take off, remains to be seen. But yeah, definitely, I can relate, you know, with
Yeah.
all these rumors.
Yeah, and what I'm seeing is these come in all different forms and sizes, right? Like, I talked to one of the SCU guys has some. I'm trying to remember what crash. Basically, it was like slag. It was just like molten slag, you know. If I remember right, they collected it off a tree, and then, you know, there's other stuff that's, and then on top of that, just to add confusion to the mix, sometimes there's like residue from orbs, right? So.
Orbs, like that should be different from the metallic one, right? Are you talking about the angel hair, the so-called?
Yeah.
That one.
Yeah. So there's.
Yeah, it's. Mhm. And one more kind of residue that often goes, you know, unlooked for, which also explains why, you know, recovery teams pick up even the dirt of the landing site. Sometimes you will get the, you know, the usual burned circle, the burned grass and everything. In some of the landing cases, you know, you could actually find metal inside those burned circles that were supposedly left there by the object landing. I have a sample from one such landing case from Italy, and it had a lot of, which one was it? I think it was antimony. It had a lot of antimony, like off the charts, a lot of antimony, compared to a control sample that was, you know, recovered a few meters away. So you can actually say that, you can actually, you know, demonstrate that the change in the composition can be explained by, you know, by the landing taking place.
Orestis, another angle that might be worth looking into is when you see all these different elements in your samples, try identifying if any of the major components there have overlapping Rastlalin bands, or any overlapping special terahertz related stuff. So the lattice vibrations, from what I'm seeing, I have this big, you know, list of like 36 different UFO samples, right? And when I go through that list and I look, wait, how many overlapping, you know, terahertz active materials are in here? Some of them, it's up to 5 or 6 elements, all have like the same window of, you know, a couple of terahertz bandwidth. You know, it's a wide window, but it's still in a similar range. So when I see that, when I see like, here's a sample and it just so happens that it's got, you know, 2, 3, 4, 5 elements that all have this overlapping, intersecting, you know, frequency response in the literature. When you look at each one individually, it's worth considering that maybe that's part of the function of this thing, is that it's utilizing these lattice vibrations in very unique and complementary ways with each other.
Yeah, you would, of course, you would need a terahertz laser to, you know, look into that more. No?
Well, yes and no. So if one way to do it is, yes, you pump it with a terahertz laser, but we're talking about optical phonons, right? So it's like before it goes into chaotic phonons, right? It's like coherent phonons. So chaotic phonons would be like heat, right? So it starts out as a coherent lattice vibration, and then eventually it decays, actually very rapidly, it decays into heat. But in that minuscule amount of time before you get a decay from a single pulse, that's where the special effect seems to take place. Well, there's a lot of different ways that you could end up pumping that in there without having to have a big giant, you know, laser or optical phonon transducer or something. Like, there's other ways of doing it. So ignoring the how for just long enough to go, what does that mean, might produce some fruitful areas of investigation in some of these samples. Not all of them, especially the more biological it is, right? Because we're talking implants, the more difficult it becomes. But the sheer fact that you have heat as being, you know, in that somewhat similar tens of terahertz range of, you know, frequency, it could be down converting it. There's a lot of stuff there, but there's this magic window of terahertz that's worth investigating to see overlapping responses of the materials involved.
Yes, there are some patterns. You're very much correct. There are a lot of patterns actually that seem to be pointing, you know, towards the same framework. Like, I've seen layers in my own samples, like in arts parts, you know, not bismuth, magnesium, zinc, but others, you know, with iron and with some chromium in them. Some of them have chromium, some others don't. Some others are pure iron. Yeah, definitely. Definitely. And the fact that you only see those layers when you break that piece from the bulk sample is even more strange, because, you know, of course, it's the way that the metal fractures, but that's the only time you see those layers. And arts parts is a fragment, you know, so that's also consistent. So maybe if we were to find the bulk disk where the arts parts came from, the microstructure would be very different. Something to consider. Yeah.
And whenever you see layers in any of your stuff, that's when you know that it's doing the same thing over and over and stacking the effect.
Yeah, or taking advantage of some capacitance that's in there, maybe. Yeah. Larry.
Yeah, what if this is just speculation. What if the material was irradiated at different frequencies in a vacuum or in a controlled environment? Each element, chromium, you have your chromium isotope, your titanium, and all of them and they were excited at their frequencies, and then in the basis of time, maybe the timing of when they come together, when you go to molecularly fuse them together, that this is the way they overlap them, possibly using frequencies and then maybe heat a little bit at different temperatures and different voltages, possibly. Even voltages and current would definitely probably be involved in something like this.
So you're describing something that's similar to the Philadelphia experiment effect, right, where materials fuse, right, by supposed electric magnetic fields around.
Yes,
right?
similar to
If I'm
that,
getting this
except
right,
it's in
yeah.
a controlled environment state. That's what I'm describing. Because I've seen pictures of laser casting where they take powders and chemicals and they put them together, and then they, using lasers, they fuse them together. And when they hit certain temperatures, and it's all done by controlling the timing of it all, they fuse together and they come up with a strong molecular bind in them.
Yeah, that usually just melts the powder, and the intermolecular forces fuse them together and bind them in place. But to test that hypothesis, it would be worthwhile to do SEM mapping. So the scanning electron microscope has a mapping feature which can literally map the elements of one area of a sample. So yeah, you could do that. And if you observe layers, for example, that diffuse into one another, then you can say that it points to that direction. Yeah, why not? I haven't done that so far, but it is in my to-do list. Not just for the layers, but just looking for something interesting, something different that we can dig into for more data. Yeah, it's a well with no bottom, basically. Yeah.
Well, I do have a little bit of casting experience. I used to run the shaft furnace in a copper refinery, and I know a lot about copper, and I know what you don't want mixed with it. You don't want iron in it when you're trying to make it pure. So when you're trying to make it into wire or cable.
Okay. Will it layer well with nickel, for example, nickel and iron? Because that's the layers that we saw in one sample: copper, nickel, copper, nickel. Oh, strange.
Yeah. Well, guys, we're at the top of the hour. Larry has been patiently waiting. So I should mention, and we'll try and work on this. So Curtis is back as well. But so George Egely, and it's a shame because before we get to Larry, George Egely, this is all news to me, but Infinite Energy Magazine, which was started by Dr. Eugene Malov, right? Larry, you're probably well familiar with him from back in the day.
I met him one time.
He was Eugene Malov. I mean, it's ancient history now. He passed away in 2004, I think. But Eugene Malov, when Pons and Fleischmann made the cold fusion announcement, they got immediately beat up by the entire scientific community, right? It was just like all out, warfare against them. And a few people came to their side, and Eugene Malov was one of those, and it really hurt his reputation. But he believed in it. He said, there's something here. And he said, screw it. Like, science outweighs popularity, And so he started Infinite Energy Magazine. He ran that for years. It was incredibly high quality. He was an amazing, courageous man. And he was actually murdered, depending how conspiratorial people are, right? But they said it was a local person for drugs, if I remember right. So Infinite Energy Magazine ceased in around 2004. Well, George Egely picked it back up and produced more of those. He took over as editor, and he has been doing that for years now. I had no idea. I didn't know they were still going. And so George has basically taken on the mantle of leadership for that community, right? Serving as like this single source for basically these scientists to communicate with each other. And it's absolutely amazing. So when I came across his work, I was like, please speak about where this is at. And so he is open to it. He is just struggling with his video system. And again, that happens. I will see, maybe we can pre-record something and play it or something along those lines. But I would recommend that everybody who's out there who has any interest in emerging nuclear stuff, take a look at Infinite Energy Magazine. From what I understand, they are going to start selling back issues online. They may already do that. There was print versus downloadable, and I was looking for PDFs. And I already told him, I was like, if you have something that I can download, man, I will pay you like 10 seconds flat, because that's the real deal. That's like real peer review type cold fusion science by the professionals, the biggest people in the industry. So that was why I'm super bummed that George is not able to present today, but we will try and get him back. And if he's not able to make it work, we'll find an alternative way to make it happen. Yeah, because, and again, Infinite Energy Magazine, that is the one to look up. They have stuff online already, and I think they're going to start, if I understand correctly, they're going to start selling their back archive or selling it in digital form, one of the two. So on that note, let me take everybody out. And Orestis, thank you. Actually, before we go, one more applause for Orestis. Orestis, thank you for presenting on the samples, and keep up the good work there too. It's so important. I mean, like,
Oh, I will.
It's out there,
You can
man.
count on that.
It's
Yep.
yeah, it's out there. It's just a matter of finding it and validating it. You know,
Ben
it's
Morton,
amazing.
sounds free.
I'm getting ready to do the presentation. One of the guys.
Seek
did
and you will
show up.
find.
Thank you.
Peace.
So I'm gonna take everybody out except for Larry. Larry,
Yes.
your patience, sir. Thank you so much. And you are my TT Brown person, but also FlameJet generator. I think that's your focus,
Yes.
today, right? And so this is actually a couple months overdue, because you had been talking about a 50th anniversary?
Yes, it's a 40th anniversary since Townsend Brown passed. He passed away, I think it was October 27th, 1985, and we just passed that. So it's kind of a celebration in a sense. And
Yeah.
with all the things that happened with Townsend Brown in the last, especially last year with Drew and Dr. Bueller, and then Mark Sokol and them showing that his stuff working in a vacuum, him and Wayne O'Hala. It just kind of came together all at the same time. So
Yeah.
it really did.
Well, if it's okay, I will take myself out. I will be here. Do you have anything to show? Do you need to put a screen up at all, or? Well,
I sent you some. I think you got my presentation. I think I sent you one, and then you have the old one, whatever one you want to use. The other one doesn't have all the pictures that I had. I reduced that down to just a few in the presentation that I sent you.
I have a January 2026. Yes. So let me slides and PDFs, your computer. This will take about 2 seconds. Sorry, I had this on my other computer in the house, and
Okay.
forgot to move it over. Yeah, so it should be right there. So this, and I'll put this one up. And so for this one, then just say, next or previous, and we'll kind of roll with it like that. Okay. There we go. Is this the one? Yes. Yeah. So I'm going to check myself out.
Either one will work. It doesn't have as many. We'll go through this real fast.
Okay.
And we know that Townsend Brown was born in March 27th, around March in 1905. And of course, he died just in 1985 at the age of 80 years old. And last year, October the 27th, became the 40th anniversary since he passed. Next slide. That's picture Townsend Brown. Next. What we were going to, originally I was doing a 40th anniversary presentation. I was going to cover the early life of Townsend Brown, and in it was going to be the early life, the curiosity that Brown had when he was a kid, how he got into electrokinetics or electrogravitics. Both terms are, gravitics is the one most people are familiar with. Then in it, we'll go through you have the Coolidge tube discovery, the Caltech rejection, where he got rejected by Dr. Millikan, and then where he returned to Denison University with Dr. Paul Beefield, and then how he came across the Beefield-Brown effect, breakthroughs and patents, projects, Winter Haven a little bit, Bonson Laboratory, and then his Navy involvement, and then final years. Next. Townsend Brown was born in, of course, we said earlier, Zanesville, Ohio, 1905, and he was fascinated with electricity from childhood. As he grew up, he became interested in electricity, electronics, and radios, and he was supposed to be the first person in Zanesville, Ohio, to build a radio when the radio came out. That's one thing I've learned about him. Next. He attended Doane Academy, which was linked to Denison University when he was in probably middle school. It's like a private school. It went all the way to high school. Of course, he had a strong interest in physics and electricity, and he began to build and test devices, simple high voltage systems back when he was actually started, I think, when he was 10 years old. Next. This is Townsend Brown and his dad, Lewis. And this is him when he was probably about 10. Next slide. That's him at 14 years old. In the background, he's on a Curtiss aircraft. He actually had a little course he took as a teenager that where he understood how aircraft flew. Next. Townsend Brown was, of course, we know that he was a pioneer because he was a pioneer in the foundation of electrogravitics, which later became kind of involved into electrokinetics. His work was, of course, overlooked by mainstream physicists at the time. It was a foundation for future of non-fuel propulsion systems. And of course, his discoveries are resurging through modern replication. Next slide. Now, the initial discovery of Brown started with the suspension of a Coolidge X-ray tube on a string. And I think he kind of got this from maybe some science fiction ideas of the time, because when growing up, there was, of course, Jules Verne was some of the people he had notably read about, Tom Swift, and of course, H.G. Wells' material. But he got the idea of suspending a X-ray tube on a string, and then when he turned it on, he noticed it moved. At first, he thought it was the Coolidge tube doing it, but after he got to investigating, he realized it was coming from the capacitor. And this is kind of where the idea of electrogravitics had got started. Next slide. Here's a picture of a Coolidge tube. This is just a vintage picture of how big they were back in that time frame. Next. In 1922, Townsend Brown applied at Caltech, and he went in there with the idea that he thought that maybe the staff, which was headed by Dr. Robert Millikan, would be impressed with this stuff. But the exact opposite happened with Dr. Robert Millikan. He was a Nobel physicist, and I believe in optoelectronics is where he had got his work that actually supported Einstein's theory of relativity, is where he got noted and was given the Nobel Prize for that. But he went in there and he was not open to any new ideas, especially from a student. And this rejection kind of affected Townsend Brown in two ways. First, it kind of knocked off his pride, and but that also made him realize that not everybody's going to believe in the things that you're doing, and it also caused him to become very determined in bringing forth this new field of energy. Next slide. Here's a picture of Dr. Robert Millikan at Caltech about that same time frame. Next slide. After his rejection from Caltech, Brown enrolled at Denison, and it was there that he also, about that same time, he started to work in that kind of part-time in at Swayze Observatory, and he noticed that Paul Befield, of course, shared a lot of similar ideas to gravity that he had shared, and this is why that's probably why the both of them kind of met up and kind of got to know each other. And it was Paul Befield that actually suggested the experiments that Brown did later, which are noted in his patent, British patent 300-311. And there is, for the longest period of time after he left the Denison University, the records kind of disappeared. But Paul Shefskin was able to relocate the recommendation by Dr. Paul Befield for Brown when he went into the Navy. So he was vindicated there. Next slide. Birth of the Befield-Brown effect. Well, after he had done some of the tests, he found that that asymmetric capacitors produce a directional thrust, and this was observed in the air. And also, he made a vacuum tube, and he actually noticed it in that vacuum tube, and he noticed this in the original patent, the British patent 300-311. The force would increase when the voltage would rise, and if you kept a dielectric separation between the plates, and the stronger you kept that dielectric, the voltage rose without breaking down or arcing over, this effect would get stronger. This became central to Brown's life. Next slide. Okay. It was the revelation of the Befield-Brown effect that, of course, established the foundation for the further research later on. Next slide. Here's, of course, many of y'all have seen these pictures. This is the British patent where it shows these plates, and it shows each plate. It's actually going negative to positive, and when you'd apply the negative charge to the positive side, it would move in the direction toward positive. Of course, you have the one he did where it was immersed. In one of the tests, they did an immersion where they did it in a tank, and he got up to as high as, he said, 300, I think it was 350,000 volts. And then the next picture over here shows the two lead balls that are separated with a piece of glass rod in between them, and it would when he jolted it would move. Next slide. And then, of course, this is, you've seen this. There's a photograph of it later where he had built these two gravitators, as he called them, and they would spin. Now, the gravitators themselves were lead oxide plates originally separated with, between them was about an 1/8 to 1/4 inch of what they call empire cloth back then, which was, empire cloth was used on a lot of the old early wires for insulation, and he soaked these in several places. He soaked them in oil, but other times he's beeswax, and then he covered these again with shellac, and then it was bakelite on the outside, and then there was a small gap on one end so that if it discharged, it was 11 thousandths of an inch wide. It was to keep it from being over voltage. But like I said, when you devote the negative charge to the positive, it would move in the direction toward the positive charge. And in the next photo, you'll see this picture here of this drawing illustration where he's in his lab at his basement in Zanesville, Ohio. Next slide. Yeah, here's the construction of the asymmetric capacitor. Shows it a lot better here, a lot closer. The next slide. That was the rectangular one. They also built some round ones, and it's still the basic same principle. Next slide. Here's the vacuum tube, the one where he had it back in a vacuum, and he had a negative charge going through the vacuum and then going to the positive side. I'm kind of surprised on this because he showed this, and when he first came out with the patent, immediately he was accused of an ion wind effect. And this kind of shows that, well, ion wind has to have an atmosphere before it can go through the atmosphere. Next slide. Here's the photograph of that picture I was talking about. Down on the bottom is the high voltage source going up, and you can just barely see the lines in it where it hangs. And but this was in the basement. I believe it was in the basement of his house in Zanesville, Ohio. Next slide. His next patent was the 1,974,483 U.S. patent electrokinetic generator. This is the first time he uses the word kinetic in his patents. And in this patent, next slide. I don't know if you can see these or not, but in them, he had already reduced, it looks to me like he had already reduced down to one single electrode, and these were longer, and there was a separation between the positive and the negative there, but I think I can't see that real good. The figure on the bottom side there, it was more like a fan shape, more curved. And whenever I built some like this, similar to this, and Tim, the first time he came and photographed them, I had them on my table, but they worked pretty well. They were a little bit different, but they did work. And he had these in a circular form to form a motor so that it would spin like a motor. And I think this is where he got the idea of rotating everything in a circle. It worked. It worked for the time. And then he shows one of them's a generator and one of them's the motor, and the generator works, I think, kind of opposite of the generator, but it would generate these fields. And it looks like he had on this bottom part, he actually had several of them to form a motor that could actually do some work. Next page, I'm sorry. Yeah, here's a better version of that. It shows the the negative charge spinning and the generator spinning opposite in the generator, and then on the other side it shows the motor turning toward the positive end. It's just kind of reversed on this other side, on the generator side. Next slide. And of course, this is the probably one of the most famous patents is 2,949,550 from Project Winter Haven, which was used to interest the U.S. Air Force and Navy into his research. And there's, of course, pictures of this where the apparatus is, I believe that the one on top was actually like 17 feet in diameter all the way across. And then these 3-foot discs were at the bottom, suspended from poles from the top. Next shot. Yeah, this is the side view of it, where he shows one side the negative and the negative separated from the positive, and then they show. And this in here shows a power supply being built inside of it, kind of, and as an illustration of how it would work if it was going to be as an aircraft or a moving vehicle. Next shot. This is another part of the patent. It just shows this is more for moving. I think this is described for moving fluid. It can move air or some kind of solution through space, and the power supply. It shows the high voltage power supply being hooked up on one negative and one positive. And then this, of course, is where from the negative backside, it would flow over to the front, or it would go from the negative charge to the positive charge at several thousand volts. Next slide. Here's another illustration of it again. This is the one everybody sees. You've got the negative charge coming off of the back with the arcuate electrode with a negative charge that's grounded to the center, and then you've got the positive on the front separated with a dielectric separation between the two of them. And again, it's the same thing. It's just showing it how it would work in real time. Next slide. This is the notes that Brown sent to Tom Terman. Tom Terman was an electrical engineer, and he had conversed with Townsend Brown several times, many times, in fact. And Tom Terman was told by Brown in 1967, after several times that he had written him, about 1967, Brown finally told him, he says, "I can't talk to you anymore. They're pressuring me to not talk about this anymore." And that was in the more advanced stages of his research. Next slide. These are two gravitator saucer discs. This is probably late 40s or early 1950s. Next slide. Of course, this is the construction of one of those in his laboratory, and originally he used plexiglass, wood, and then plexiglass for these, where he would put the arcuate electrodes. Next slide. Here's a famous picture of Brown holding the 3-foot disc capacitor. Next slide. And of course, this is him in the laboratory testing them. And I believe this is in Long Beach is where this is at, where this picture was taken, California. And you can notice, one thing you'll notice how big the power supply is that he used for these bigger discs. Takes a little bit more watts to move a little bit bigger size disc than the smaller ones. I first started out building these discs per scale, and I made mine were 1.5 inches in diameter for the first ones that I built. And I was just under 50,000 volts, about 40,000 volts. And I was able to get it to work pretty good, fairly about 1 revolution per second. And then later, the biggest ones I made have been 6 inches, but I made some that were heavier, that each one of them weighed 0.5 pound each, and they were very thick and blunt on the ends. And I think I got the best out of those. I actually got the best speeds out of those when I was testing them at home and when I lived in Amarillo, Texas. Next photo. Next. This is another one I built. This is the one this is a picture of the one that Tim took a picture of, and I just showed this. In this particular one, I had sealed off the high volt. I used some real high voltage wire with insulator on it on the front, and then I sealed it off with silicone and the plexiglass. I had it attached to the plexiglass. Well, standing right across from me was Tom Malone, and he was watching it run, and he said, "How come you got this high voltage? How come you got that glue to that? It's conducting through the plastic." Well, of course, I looked at him and I said, "Well, it's sealed off." He says, "No, it's conducting." Later on, I found out that Tom Malone was partially right, because whenever you get a high voltage stream across plexiglass past about 70,000 volts, it will actually form a piezoelectric field effect, and it'll actually move. But it was actually moving, and it was working. It worked pretty good. But I just wanted to note that. Next slide. This is Paul Lavalette's explanation of the B-field-Brown effect in subquantum kinetics. I was going to pull that up. We'll go to the next slide. Okay, this is the G-heel. This is the G-heel that was talked about by Brown, and Paul Lavalette put it in an explanation in his books, the Secrets of Anti-Gravity Propulsion, and also his Subquantum Kinetics book, where he shows a high K dielectric with a force, and then with a G heel, and then a G well, gravity heel, and a gravity well. And I think this could be argued here. Some people would say, well, this is like warping time and space, but Brown kind of led to that, but there's a lot of controversy about that. Nevertheless, we know that when you have a strong dielectric and you have the high voltage, that it creates kind of a damming type effect, and it does move from the negative charge to the positive side, positive force. Next chart, next picture. This is the this is the patent that, this is the one that I built later on, of the U.S. patent 3,022,430 electrostatic generator. And I built this, I built this as a generator. I did not build it as a propulsion device to move stuff. I just wanted to see if you could build it. Now, I did, in my pictures, if you what I did was I actually used coffee cans and then drilled different size holes through it to expand it out. It got up 3 or 4 different sizes, and then it came out. And I had 20,000 volt capacitors between each one and every one of these. And on each side, I had 2 sets of them. So on each side, I had about 260,000 volts, roughly. And on my discharge of where I had the charge from it, I got about almost a 6 to 8 inch spark. Got it that long on the going from that to the grounding plate. Next slide. Yeah, this is the downstep generator, and I built this when your high voltage system hits the. I built a little grid in it, and then I had this hooked to some other series of capacitors, and each one of these capacitors are different size. The incoming one was 20,000 volts, and then the next one was lower and lower and lower, and then in between here, Brown tells you to build a spiker. It was a spiker. It's like a point system. It would spin around, and it would discharge this. And on my particular research, when I was doing this, I was like all the way down the last capacitor, which was 50 volts. I was getting about 14 to 20 volts. The only thing wrong with it was the spiker wasn't working that good. I was getting the amperage from the ionizer that was coming out of the top of the burner there, and that's what I was getting. I was getting seven. It was showing just under 7 milliamps on the discharge side. So the spiker wasn't working as good, and I think in this particular instance, with modern technology, would probably be better to build it more like a digital type of system to go in there to switch it. And I think it would work better and be a lot more efficient. Next slide. Of course, this is the patent 3,187,206. This is the first one. It shows the column, and Brown found this middle column. The first time he did it, he just used a Pyrex glass. It didn't have any kind of dielectric around it. The one thing he noted in there is that ball on the bottom end need to be bigger than the column itself. It needs to be in circumference, and it would. And he said that you didn't want it. You want to make sure that the conduction went through the rod, and you were able to control the timing of this so that the voltage built up at the top into the curved dome or cubic that you have at the top. The bottom side, he also showed the T here in this. He did the same thing, and of course, in Project Winter Haven, there were very different variations of that. There was 1, 2, 3, 4 different balls that were on the bottom, and then later, after Project Winter Haven was complete, he started applying the barium titanate that he used on the column, and it's my understanding from Kitzelman, who had witnessed this, Au Kitzelman, who was a good friend of his. He went to Washington, D.C. to see Brown do this. And the first time he saw it had the demonstration when it, I think this dome that he had made, when he applied the voltage to it, it produced about 100 grams. I think he said 100 grams of thrust per Newton. And then later he was able to get he claimed that he was able to increase it up to 400 grams. Next slide. This is the famous wedge shapes. I always like to use this kind of as a version of that. In this, the negative charge is on this side, the positive charge on this side, and it would move in this direction, I think. And he has different pictures here. He shows the same thing using a coil version of it, where when actually when the positive was below the curve, the flow of electrons would go up and it would raise it up that direction. And this, of course, is with a series of them put together to create movement, or like a kind of a transduction effect. Next slide. This is a picture of my FlameJet generator. This is the one I built in 2018. And all this stuff, what you're looking at here on the little red at the bottom are the capacitors, and they're sealed in wax. They're attached in between each one of these plates. And I had 12 plates. The plates were just simply to hold the cans in place. And then I wrapped muffler tape around that and sealed it to form to run the flame through. And this stuff in between that is actually ceramic fiber. We used to use it in the casting operation at the plant. It has a melting temperature of about 3,200 degrees Fahrenheit. And below that, you can't see it, are the controls. Next slide. This is looking at it from on this end closest to the end toward the bottom is where there was a blower I had in there, and I tried to use a blower, and then the high voltage power supply came in there, and I had the needle right dead center where the flame would charge it up and it would blow through the tube. Next slide. Yeah, here what I used originally was just a Bunsen burner. It worked pretty good. The problem I had though was you had to have that where the needle came out. You didn't want it too close to any of the metal because it would start discharging off of it. And I was able to overcome that by putting some insulation around it so that it would continue and blow through the tube of the burning tube. Next slide. This is the exit end, and this ball on the side over here is the discharge. I had a plate a little later. I built a grid, and the flame would hit the grid, and then it would discharge, and then it was hooked on the balls over here. The balls were just how I used them because they work real good with high voltage electricity. Next slide. This is the pulsar I built, and right next to that are the series of capacitors I had. I had I think I had eight or 10 of them, and they, like I said, 220,000 volt capacitor, and then it went through. The next one was 500 volts, and then it dropped to 250, all the way down to 100, then down to 50 volts. Next slide. There's the grid. that's the grid that I made for it. Unfortunately, I lost all this stuff. I was up in Michigan, we had a fire, and I lost it in the fire back in October 2018. But it was after I'd done the presentation at Ellswick's Tesla Tech Conference. Next slide. Now I'm going to stop it right there because this here's part 2 of the whole presentation. It's just more or less about Brown his life going into the Navy. But I'm going to stop it here, and anybody wants to ask questions about the FlameJet generator, they can go ahead and we can go ahead and pull them up, and they can do that.
Okay, Larry, amazing, man. That is so cool. That is so cool. Thank you so much. So before anything else, without any further ado, let me see, this is the guys who were with us. Oh, and there's Joel. Okay, guys, put your hands together and give an enormous applause to Mr. Larry Deavenport. Larry, that's way more extensive. That was an awesome 40th anniversary presentation. Thank you.
Well, thank you.
Yeah, and if you want, you can go through the rest of it, or we could just do Q&A. I know that your FlameJet generator is like, you did a great replication of that. You showed me the photos, and I think I saw some video too, and that was amazing.
Yeah, I think you've got that, but I don't know if we've got it on this computer. Maybe it's your other one. I think I sent it to you before, but it's a lot more pictures, and I didn't want to, because of time, I just decided to get to there and stop, because the other part of that presentation is more about just the life of Brown, and it was it goes into a lot of when he was involved in intelligence and stuff, and it would have taken another hour, so I thought this would be a good stopping point.
Yeah, well, and it might have confused people too. He was one of those. Brown was like prolific, right? He was everywhere, and when he got popular, everybody wanted him to work on their stuff. So,
yeah, and he when Paul Shatskin was there with you and me that year that you recorded the electrokinetic apparatus, and after I did my presentation, he came up to me and he corrected me on something. I can't even remember what it was, something I said, but it took him 20 years to write his book. That's this in here, the Man Who Mastered Gravity.
Mm.
And he ran into, when he went to check out Townsend Brown, he ran into brick walls. And we tried to get information on him that it either be classified or blacked out. Luckily, a former boyfriend of Linda Brown's, he goes by the name Morgan, and they never do tell you his last name because he was still in high up in intelligence, was able to get a lot of the material for him.
Okay.
It's not the same book as like this in here or Electrogravitics by Tom, but it really makes him more of a family person when you read the book. It just kind of he was human. He made errors. We all do. Things he regretted. We all do. So if you want to just learn about his life, and it's a lot of it's about Linda Brown trying to help him. Read the book, The Man Who Mastered Gravity.
Awesome. Well, thank you. Thank you.
Yes.
Yeah. So what dielectric did you use?
Dielectric. I just use the ceramic capacitors. For the FlameJet generator, those capacitors were 20,000 volts, 0.00 microfarad, 20,000 volts each. And when you charge them up, when you run, it actually worked better, believe it or not. When I was doing the demonstration, I also had it hooked up where you could add CO2 through it. The CO2, I think, worked better than the gas, because the heat factor with the gas kind of fluctuated it. I think the CO2 gas worked better, or is good. And what I thought I might do later, if I ever have time, if not, maybe one of you guys can do this, is if you could build a unit that's in CO2, maybe with a light pressure on it, and build the same type of effect on it and have a fan built inside of it and have it sealed, you might be able to build a type of generator. And then you could inject purge out the oxygen in there and then put in the CO2, and it'd be like an enclosed system. Then it could work like that as a generator. Just a thought.
There seems to be some advantages with some gases. Like I think I remember reading in that book, The Secrets of Anti-Gravity Propulsion, that if your gas is incompletely combusted, it sort of creates some more massive particles that add to the push, to the force. I don't know if you had any observations with that.
I just used natural gas on mine, and then I had it where I could adjust the flame down. The advantage of using those Bunsen burners is you can adjust it. You can make it heavy, you can make it orange, or you can make it blue, but it worked both ways. Brown actually suggested it more more fuel rich than oxygen when he was doing it. And that might have been because of the carbon. I don't know if it was the hydrocarbons in the gas or really what it was. But anyway, at least I was able to show that it worked. That was the main purpose of building that.
Definitely. I asked because I had come across a few papers by various teams, nothing to do with electrogravitics. They were just doing research on capacitors, and I would see the dielectric constants being crazy, like in the billions, but in low frequency though, right? So about 100 hertz, very low. But I suppose that with so high a dielectric constant, you probably outweigh it probably more than compensates for the low frequency. But these things are very expensive to build. That's the problem. That's where things stop for the most part.
Well, I consider myself lucky that I was able to at least fund myself when I was building all that at the time.
You definitely did more than a lot of people ever will.
Sure.
Yeah, Larry, outstanding presentation. I really want to hear from Drew. I'm sure he's got questions, but before he gets to it, just one question for you. What would you say in all of your testing and your research on TT Brown stuff, what was the result that you produced that you felt the most proud of?
I guess the first time that I found out that it worked was and that was way back 30 years ago. People were trying to do Townsend Brown stuff. A lot of them were trying to do the lifters, and I'd done those before the lifters. It was when I built the electrokinetic apparatus and was able to get it to work. The patent 2,949,550. And then I did it scale at first, and then I noticed as bigger you got, the bigger, of course, the larger the disc got, you had to get a little bit more wattage. And at one point, I even tried to build some ceramic covers on top of the disc, but there was too much of a dielectric there, and it just literally would stop it. So I knew then that the dielectric, when he said that you had to get the higher voltages, the higher you went with the voltages up, that you've got to be able to overcome your dielectric effect. You don't want to go too much on that. I really don't. I think people, and probably Drew could probably answer this better than anybody, because since he's here. In a vacuum, it seems like it works better than it does in the air. However, the FlameJet generator, I get why Brown leaned that direction. Jet propulsion was coming up. It was coming up, and he saw it as a means and ways to get electrogravitics into the using it for jet engines and stuff like that. And Of course, we know that from Paul Lavalette and then from Aviation Weekly that apparently they were using brown stuff in the stealth bomber, and it's supposed to be covered. I think it is covered in barium titanate, and then on the front edge, I think it's actually got diffused uranium on the leading edge. And I think the main reason they used it myself, the main attraction for the Air Force was to make a craft that was radar invisible. And of course, the ionization of the gas was an extra plus. It actually helped the craft move. And I think that was, but the main reason I think they chose that design and it was for deflection or radar. When they go to build strategic platforms, military doesn't always build the fastest. Sometimes they'll pick things slower. A good example of that is the A-10 Warthog. It doesn't go as fast as the F-16, but it can take a shot that none of the other planes could take. And it can go low in, it can go in low under radar. And that's the way they design things in the military.
And if I could ask a follow-up, if you had all the resources available to you, what experiment would you love to see? What experimental setup would you make as like the best thing that you think you could make with all the resources available?
Oh, wow.
For the best possible TT Brown thing you'd love to see?
I would love to improve on the FlameJet generator. Probably that would be one thing I would like to improve upon. And that's just my personal wish. And I have bought some other capacitors that are bigger. I've got some 50,000 volt ones, but then you've got to have a bigger FlameJet generator and a bigger source of a higher wattage coming out of the power supply, because you're making things bigger, and it's just that only stands to make sense why you'd want to do that. But if I could get then if I could get the stalker working right to see just exactly how much efficiency you could get off of a generator, because I can see a use for this as the voltages get smaller and your microwave, like your phone and everything are getting smaller. You could use high voltage electrostatic electricity to transmit it several miles and use it to charge up things like your phones and things like that.
Yeah, the thing that I like about the TT Brown FlameJet generator is it's kind of this old school approach to things that it's more of like a mechanical engineering approach to things that folks don't think of enough. Like I was reading about Tesla, how he tuned a Tesla coil, right? Because you do the math for that and the math sucks to tune a Tesla coil. And they were like, well, how did Tesla do it? Well, he would get the coil wrapped, he'd get it built right, he'd take his pancake capacitors and he would turn them kind of like a vise. They would slowly come together. And when it went resonant, he could see it. And, it takes that incredibly difficult process of let's do the math, let's do the dimensions, all that. And it's just like, hey, I'm just going to keep turning a little crank and at some point it'll work. And like the FlameJet generator is kind of the same thing. It's like mechanical charge separation, right? It's like chemical mechanical charge separation. You're putting that high voltage into a jet flame, and then that mechanically adds energy to it. So you don't have to deal with like bulky step ups and Jacob's ladders and stuff like that.
Yeah, I've built Tesla coils. I know the biggest one I built was 650,000 volts with a rotary gap in it. So I know what you're talking about there.
Yeah. Well, you guys have any more questions? I think it's almost 3, so we're running a little ahead of schedule today, but that's not bad at all. So
Yeah,
me a minute.
just in time.
But I think it's very good that we have Townsend Brown on Rich here, and we continue to talk about his topics, because he was a pioneer in what we're trying to do. And yes, it was a really interesting presentation to recap his history.
Yeah, and it's such a shame that these things are not explored into more openly, more on a massive scale. Like allegedly, that's why those engineers came out to that magazine about the Beta 2 bomber. They were like, it's so simple to make, it would help the world. We cannot stay silent, right? Like, yeah, you just wonder.
Yeah, well, Larry, we're just about so Larry, I think Orestis, you had one more question, and then.
Yeah, just another idea that I just came up with it actually. Like, have you ever thought of making like smaller FlameJet generators, but attaching them to helium balloons, for example, to reduce their weight? And that way, if you stick them together, you can make an apparatus rotate, and that can generate electricity, which can then power the generators. If you think about it, just an idea.
I've thought of a lot of uses for the FlameJet generator, and I also thought that using electrogravitics instead of having to use helium, maybe you could, charge the inside of a balloon somehow. Maybe have a conductive surface on the inside, and have your at the bottom have your negative charge. It would actually act like a balloon, but you wouldn't necessarily have to have gas in it. But I don't know if that would work. Drew's saying no. Wouldn't work.
Okay.
I want to hear your input.
Been there, tried that.
Oh, you did?
Yeah.
Okay, that's all he has. That's what he has for us. So.
Yeah. Yeah, it's interesting. I looked over a lot of the TT Brown stuff, and I threw out everything that had to do with atmospherics, because the ion wind is probably, I don't know, 10 times, maybe 100 times the force of the electrogravitic, even though that's not real. So when you start putting gases in there, and anytime you can generate ions, you're just messing around with action reaction.
Okay.
I just discounted all that stuff. I mean, it all works. I mean, you put 1,000,000 volts on one of them discs, it'll fly across the room.
I was getting up to three revolutions per second on mine,
Yeah,
and it was on a 3-foot.
What you're doing is you're just building a really clever electric ionization. It's Sharper Image used to have an air filter called the whatever it was. Okay, no moving parts. I mean, it just blow basically whatever it was, ionized air, ozone. It blow ozone on you basically. Yeah. That's what it's doing, and then they come to find out that breathing ozone is a really, really bad idea. But the point is, it's not very effective. It's not very efficient in the use of power. So even if you built a really sophisticated ion wind fan, let's just say somehow magically you built one of those, you're better off with a little spinny electric motor. It's just pure use of the energy. I mean, it's novel if you don't want to have electric, if you don't want to have, mechanical spinny things or whatever, generating torque and moving and compressing air and stuff. It's very novel. With it, maybe I'm missing something. I don't know about the whole B2 bomber, B1 bomber, F whatever. I don't know what they did with that. So I maybe I don't, and I don't really care because like I said, I didn't really look at anything to do with air.
Yeah.
But when you get into vacuum, all that TT Brown stuff goes right out the window, and it all just becomes a matter of area. So if you want to have your balloon, the answer to that is something akin to a solar sail. If you started with a solar sail, and because that has an enormous area, they say 10,000, and you put a whole bunch of point source high voltage like pins, so that you basically had a whole bunch of pins and in a great big monstrous area, that thing would go, it'd fly towards the big area. So if you want to build a solar sail to go to the nearest star, that's perfectly doable. You could get up to I did the math once. It's like 90% the speed of light on the energy in your cell phone. It's still a 4.8 year trip to Alpha Centaurus, but it's perfectly doable. You could do it on a credit card size thing, or you could do it on a solar sail size thing. But again, as soon as you give up air or any kind of ionizable gas, carbon dioxide being amazingly good, by the way, then once you give up air, it's 100% area. It's 100% whatever it is, electrostatic pressure at that point.
Electrostatic pressure, yeah.
And so,
well, yeah. So guys, we're past the top of the hour. So why don't we do this? Let's put our hands together one more time for Mr. Larry Deavenport. Larry, thank you. Thank you. Thank you. That was awesome. Thank you for that wonderful walkthrough. And I guess we could just go into lab presentations. We've already slid into that anyways. Drew, do you want to do an update on what you're doing for us?
Yeah, sure. Just give me 1 second.
Oh, okay.
Just give me a second to well, I guess I can kind of I'm back to building. I don't know what you can see.
Okay.
Yeah,
I'll just maximize it. I'll be right back.
Yeah, this is my metallizing chamber, and it was state of the art for the 1980s, which I'm not real excited with. So I ripped apart all of the garbage electronics.
Oh, I
and I
didn't
went
take it.
manual on everything. So I just kind of jammed that in there and opened the plate valve on the very bottom. And all my valving is manual, and it seems kind of 1940s, but when you do prototype, you want to have control over everything. The final goal of all of this is, if I can just point this down, and I'm hoping y'all can see it. The final goal is to drop the pressure of the system down to 10 to the minus 4. It's at 10 to the minus 2 right now. And it'll get there in a few minutes, maybe about 20, 30 minutes. And then inside ye old chamber, which I doubt I can get a good view of. Let me try this. So, I don't know. Hoping you're seeing something. I can't really see it. But the whole goal of it is to metallize the surfaces. And then Santa was very kind to me this year. I think I bribed him, but it's really cool. And if you got a spare $12,000 laying around, everybody should have one of these. You got a spare $12,000 laying around.
Wow.
Thing is bad to the bone. I put a vacuum chuck on it, but this is a UV engraving laser. This is the Com Maker one, which is pretty nice. It can do about 9.5 inches by 9.5 inches, and the beauty of this is you can take just any kind of material. In this case, this is just a metallized polymer, and you can put it on there, close it all down, run your little program, and you are rewarded with laser stripped amazingness. So that's kind of a very cool toy to have. it just, you know, increases your capabilities. And I kind of consolidated a couple of labs worth of equipment. This is my CO2 laser. That's 120. I think it's 120 watt or 130 watt, something like that. So that's a bad to the bone CO2 laser for, you know, up a little higher up in the frequencies. This is my Mark Forge. This thing can print in nylon or Ultim or PEEK if you're crazy enough to purchase PEEK. And the cool thing is it can actually put carbon fiber. This is a roll of super, super thin continuous carbon fiber, and it can actually embed the carbon fiber down inside of the what you're printing. While you're printing it, it kind of just like shoves it down in there and then goes along and puts it in, and then it cuts it and then goes to the next layer and does the other things. When you get finished, if you're printing in PEEK with carbon fiber reinforced PEEK with carbon fiber, then you can actually exceed the strength to weight ratio of aluminum and the static pull capabilities of aluminum. So you can actually print parts stronger than aluminum. And of course they're, you know, non-ferromagnetic. Got a 3D printer over there. Kind of goes with the other toys. It's kind of hard to see, but there's another giant 3D printer hidden under there. And let's see, I see Mark doing this all the time, so I'll just kind of walk around the lab. Make him jealous. This is the new system where I can put thruster plates and then read them out here. And normally there's a laptop sitting there which has this camera, and there's a camera down here, and they both show up on the screen, and I actually do time-lapse movies of thrusters running for up to 24 hours at a time, gaining more and more thrust and actually pulling up, and they push down. So it's kind of cool to see thrusters operating in open air, much the way they do in the vacuum chamber. A lot less voltage because they're real easy to short out in open air. But you know, more printers. You know, the nightmare of before Christmas, which is manufacturing. So that's what's going on here in sunny Florida. Back to you, Timothy.
Sorry, didn't have my mic on. Thank you. And then at some point, and this may be in the next couple of weeks, I want to sit down and record with you, and you could do a lab walkthrough with us and all of that stuff, and do the Q&A. So one of the things in terms of APEC, there are a couple of media outlets like MSN, I think, just dropped a Charles Bueller special, right? Which is really cool. Charlie is your partner, and he is super awesome. But like, he has become the focus of that. And I guess it makes sense. He's a NASA physicist. He's their top electrostatic guy. He's got projects on the moon. That is really amazing. I mean, he is a dynamo. But at the same time, I really wish that the media would focus more on you, because you are in there building, testing, refining, and doing hands-on work day in, day out, every single day of the week. So it's kind of like this lopsided presentation. And so my hope is to be able to kind of sit down with you and just, you know, hey, guess what? It's not all Dr. Charles Bueller. There is a team at work there, you know?
Yeah,
And-
it's all
and
Dr. Charles Bueller. He's the face of warp drive. Thankfully, he replaced that other guy that was the face of warp drive. But unless you have that NASA, you know, moniker on your name, nobody even cares. You can be as smart as you want. Today, if it doesn't say NASA after your name, you are nobody, and what you're working on is nothing.
So
That's the
for
sad
me
reality.
then, I could promote the conference by getting that custodial job that I saw online. I push
Yes.
the broom and the mop, but I get the NASA hat. I'm good.
My,
And since
my
nobody
former
can check your
brother-in-law is
resume, just add the words NASA to your resume.
That's right. What do you do there? Mop the floors, you know.
my,
Yeah.
My
Now,
former
in
brother-in-law is an
Charlie's
acid scientist.
case, I don't want to make light of it. He is incredibly credentialed. I mean, he has stuff on the moon that's being tested right now. That's amazing. That is absolutely amazing. So it's not to detract from him at all. It's just that, like, when I went and visited you guys, you're a team. You're both working on this. You're pushing ideas back and forth, solving problems together, you know? So, like, I just wish that the media would, like, reflect that more in their presentation of it.
Yeah, it's not going to happen. But you know, Charlie he's on the. I tend to lead the design because I do. You know, I follow the theory of learn to fail faster. It's, you're going to fail.
Yeah.
There's absolutely no question of that. And if you don't fail and figure out what it is you did wrong and get back up on the saddle and, you know, try and ride that fucking Bronco again, then you're just going to stay down in the dirt. No one's ever going to exist. But
Yeah. Here, I'm going to mute
you know, I
Larry's out for a minute.
fail pretty fast now. When we first started out, we would get together about once a month, and we were chasing. Back then, we were chasing a dragon that needed to be killed, and it took 4 years to do it. It was wrong, and we were chasing our tails for 4 years at the iterations of about once a month. Well, at once a month, you don't get very far. And then we got it down to about once a week, and I would build whatever silly idea he had, and I would show up on Sunday at his place, and we would, you know, go through the magic of testing the thing out, and it would fail horribly, or we would have some tiny random success, and then we would chase that path, and I'd build another one over the course of the next week, and we were discovering materials that didn't work, concepts that didn't work. We finally, you know, had some huge breakthroughs, and then we got it down to he had his electrostatics lab and I had my electrostatics lab. And when I brought the testing here, which was when we started doing vacuum, the testing went to every day, and it was a different concept every day. Now it's pretty much back to once a week, but it's all week long. So a series of thruster examples goes into the chamber, which forgot to show the chamber. This is the test chamber, and it's got some coolness in there. I don't know if you can see anything or not, but that's the current test, and I literally just shut it down about an hour ago while I was listening to the whatever that presentation was just before this one, and it has been running for 6 days, almost nonstop. So I've got test data in 24-hour loops of different components that are in there. So it's learned to fail faster. 2 of the designs didn't do anything. One of them did pretty much what I expected to do because it was a base unit, and the other one was like, hey, this stupid thing is working twice as good. What did I do right, or what did I do wrong? So if I'm telling you, if you can't learn to fail faster, you are never going to succeed. I think I can't see. Is it Larry that just gave the last pretation? Larry,
Yeah. Oh, and Larry's muted here. I'll unmute him. Yeah.
Yeah.
Sorry, you had background
Would
noise.
you agree that a lot of your stuff didn't work?
Absolutely. In the beginning,
Mhm.
it didn't, and it was those little moments, Drew, little things happening, seeing a little bit of movement.
Mhm.
Like when I did I didn't even know when I read Townsend Brown's electrokinetic apparatus a long time ago, I just mechanically knew what he had done, and he gave good enough instructions where I could follow it. And because I was able to follow his instructions, I think that's why I succeeded in building the electrokinetic apparatus, the little one first, before Russell did with the big ones. Russell Anderson and we're good friends. He built the bigger ones, and he did he did a real good job with the big ones. But I didn't mind the scale. I started out small, and I started going up, and I did the same thing with the power supplies. I noticed after I got too big, if it got too big, the power supply didn't work. I had to up the wattage on them to make them work. But you're going to have probably more failures than you're going to have stuff that succeeds when you go to testing things. And you know that as a scientist, you know it firsthand.
Engineer. I am not a scientist.
Well, engineering, yeah. Yeah.
Them is fighting
right.
words.
I mean, I think probably everybody here could say the same. In my experience, back when I was building lifters, it was the same thing. Yeah, there were lots and lots of failures. You know, you have to, at the very least, and Drew, you would probably agree with this. Once you dial it in, your hit rate gets better. It just takes a long time to dial it in.
Yeah, but that's another funny thing is once you finally trip across something that works, we'll call it works. May not be optimized, but at least it does something. Don't change more than one thing at a time. I don't care how sexy it might look to change 10 things because you know what's going to be right. Change one thing at a time, because otherwise you are wasting your time. You have no idea what you just did.
Yeah.
And that took years to learn that stupid lesson. One thing at a time. And I mean, like if you're planning on increasing the voltage to something and you're planning on putting in a bigger capacitor, do one or the other. Or whatever it is you plan on changing, you change a little bit at a time, unless nothing's working, and then you just shotgun blast and try and figure out something. But once you have something kind of dialed in, you change one thing at a time. And if you buy from McMaster-Carr, realize you're never going to get the same thing twice. So be careful of your sources of materials and products and stuff. I'm not slamming them. Those guys are amazing. But you're just never going to get the same thing twice. It may look like the same thing.
Power supplies.
Yeah, it might have the same part numbers.
Yeah.
Yeah. Well, let me see. So we have, there's Curtis. Curtis is hiding out. Curtis, do you want to do an update? You want to walk us through an update?
Sure. I can share my screen, and I'll just do a quick summary of the.
Yeah, go for it, man.
The what I'm working on for the Mach effect. So let me see here. Share screen. Wow. Window. Okay. Share. Let's see. Does that work?
And there we go, sir.
Okay. So there we go. So yeah. So one of the things with the Mach effect is that Jim basically derived it from Siama's work, and he used a.
We're just seeing your StreamYard studio.
Oh, maybe you shared the window instead of the screen.
I'm sharing the screen. Let me try that again. Let's see here.
It's the time tunnel.
No, yeah, it looks like it's only sharing that window.
Okay, hold on. Let me do it again. I think it get bulked.
Here, yeah, okay.
Try again. Here. Share screen. Screen window. Oh, entire screen. There we go.
There we go.
And I can move that. No.
There we go. Perfect.
There we go. Okay, that's much better. Okay. So anyway, so back to what this paper is, and I'll explain why it's important for what we're doing and what the neat thing about it is. So Jim had derived the what I call the Woodward effect. He used to call the Mach effect, based on some relational kind of Mach principle type theories. And those theories were built on sort of a vector potential, kind of an analogy to electromagnetism instead of full GR. And, you know, Jim wanted a fully covariant theory, which is what I worked on and got done. That being said, the theory I worked on, it's very complex. I haven't gotten to fully show that the Woodward effect is something that comes out of it. It's definitely possible. And so this is sort of an intermediate step. And the reason it's an intermediate step is that I kind of consider this, the theory, it's called G4V by Carver-Mead, as it's probably the most advanced or kind of like physically sensible and engineering sensible theory for doing stuff with that takes into account inertia properly. Before I came out with my theory, so when I first came across this work, I did say at the time, hey Jim, we should go back and derive your effect from this, but I was focused on doing the fully covariant theory, right, which was more important to get done. Now that that's out of the way, and I've noticed that there's kind of grumblings out there and misunderstandings, and again, people don't understand necessarily the physical reasoning and the experimental evidence of the Mach principle, that it's not something you can just ignore or set aside. So a lot of there is a series of experiments that are in Carver-Mead's work. So I would say if you go look up Engineering View of Gravitation by Carver-Mead, his book is on the Caltech website, and it's free to download. There's a PDF, so that's a great book. And the thing that's really important about this work is that what he does is he unifies basically inertia with electromagnetism here, and also treats matter as waves. So, which is important because it takes into account some what you could consider quantum effects. And so this paper is something that I'm going to be. I have it archived in Zenodo. I'm going to, now that it's gone through several revisions. This is Rev 5. I have a lot of micro revisions as I went along, but it's ready for peer review. So I'm going to be asking people to give me feedback. But it is going to go on archive, and I'm going to be publishing it. So basically, what I've been able to do is, from Carver-Mead's work, is derive the Woodward effect in here. And so let me show you guys what's important about Carver-Mead's work. Now, his work could be considered what's called a variable speed of light type theory, because it is a vector theory. I will say that variable speed of light theories are controversial nowadays. That was what Einstein and Abraham, which is this equation, Abraham equation. He was a contemporary of Einstein's. He was also looking at a vector potential type gravity theory at the time, and that's why the equation is named after Abraham. But variable speed of light is something Einstein dropped. And the thing about it is that it turned out that GR, while it does encompass some Mach principle type effects, right, it doesn't have the full Mach principle, right? It's something that Einstein had to drop, and that's well known. So what Carver-Mead is doing with this theory is building a theory. Basically, this theory is built on top of the Mach principle as a relational effect that he knows matter does experience, right? So that's, basically Mead is doing the Mach principle side, not necessarily doing the cool gravity space bending type math here, right? And what is interesting about this is that, and there's not many other formulations or theories actually combine of this sophisticated of a view of electromagnetism and inertia. Okay, so the fact that there's one theory, one set of equations that you have, it's what makes it possible to actually derive the Woodward effect without just grabbing from random places. So as you can see, there are equations that basically the momentum is coupled to the rest of the universe. That this is a standard thing for saying that, hey, the matter here, it gets its mass from the rest of the universe, right? We know that. That's an experimentally confirmed thing. And there is a way, because the Woodward drive actually uses, and I'll go through it, scroll through this while I talk and stop at a few places. But the Woodward drive actually uses electromagnetic energy to cause a piezoelectric stack to increase, basically expand and contract. And while it's doing that, it's sandwiched between two asymmetric masses, a heavier and a lighter mass. And while it's doing that, in this theory, there's a slight mass fluctuation that happens. And you can see here's an equation for the electron's wave vector, which includes the electromagnetic potential and vector potential, okay, and the inertial vector potential, which is where what Mead calls gravitational, I call it inertial. It's sort of the same thing. You can call it inertial gravitational if you want to be strict with it, but basically this wave vector and this formulation allows you to treat these type of effects in a way that it's scientifically makes sense, right? And the theory makes a lot of sense. So of course we do have pretty much the strong equivalence principle. We have to assume that the mass is energy has equivalence, right? The gravitational mass and the inertial mass are equivalent, and we want a strong principle where that includes energy. And so we do end up with Woodward's equations at the end of the day. So, and that's what's shown here on equation 30. And this is the mass fluctuation. Now there is a difference. There is this lambda term that's a little bit different, and in Mead's derivation, that is turns out to be 0.72. In the standard Siama, kind of what Jim used, that was unity, so it was just 1. So there's a slight difference in terms of the predictions for both of those theories. So, and this is going to be interesting because once we do, I'm able to get the lab up and running again, and we do more work. You can see right here, there's different impulse coefficients, and it's about a quarter difference, 0.72 versus 1. So we should see slightly less impulse due to this, because of that coupling is derived as 0.72. So that's a difference that we'll be able to tell. And I think one of the other things I want to point out about this paper, and I don't go into great detail, but I do want to point out that there is the mega drive, which is the piezoelectric stack. There's also something called the Mach Lorentz thruster, which uses the Lorentz force to do the rectification, to get the impulse. And so that's something that I do kind of cover slightly in this paper, but that's going to be a future paper in terms of like going in detail with what that is. But the MLT is, both of them are real. I'm really excited about the future lab work, because this did turn out to work out. I was a little concerned when I first started this, that especially with the Abraham equation, and there's a Planck suppression of the constants, and it looked like things were pretty glum. It wasn't looking good at the time. This was a few weeks ago, and then I realized after rewatching some of Carver Mead's lectures, and I would highly recommend, if anyone's interested in this theory and understanding inertia, and there's a lot of talk on this conference about electromagnetic effects and gravity. But really, this is one of the few theories that actually combine inertia and gravity, inertia and electromagnetism. I mean, and inertial gravitation, right? So that this is pretty much almost state of the art, right? Other than the theory I have, which is a full tensor quaternion formulation. So this is really good in terms of that both of these effects come out of it, and they have a natural home in this theory. And what I really like about this theory is that it's much easier to work with real materials and get real predictions and start modeling things. It's much what I have in terms of the UQFT thing is much more complex, and because it encompasses even like the creation of matter and solid-atomic matter and stuff like that. So I think in terms of like the effort for the Mach effect, I think this is the way to go in terms of modeling. So that's what I'll be using in the near future. Especially the energies we have are not reaching exotic levels. So I think we're dealing with real materials. We have real forces. And by the way, one of the things in this theory, one second, excuse me. One of the things about this theory is that it does require that there be some kind of coherence, and this is why the piezoelectric stack is important, because the piezoelectric stack does have a coherent type of motion, right? It's not quantum coherence; it's material coherence, meaning that there is it acts. The structures in the piezoelectric act together when they expand and contract, right? So that part breaks down if you get heat and it starts to heat up, and that action inside the material breaks down. In the lab, we had seen that over time when the stack heats up in the drive, that the effect goes away, right? And that's predicted from this theory. This theory really does rely on the coherence of the piezoelectric stack to actually have its effect. So I'm really, this paper is really exciting in terms of a practical. Okay, I have something that's based on physics, and there's some engineering things, and I can get numbers, and I can work with materials. I can put this in COMSOL multiphysics or what have you, and actually start iterating and doing stuff. So one of the things I'm hoping to do is increase the basically move from brass to something like tungsten. Yeah, there's really, and here's the impulse equation, and here's the force, the average force equation. So yeah, it's and there's a delta M there, but yeah, I'm really excited that this all worked out. I mean, I was crossing my fingers. If it wasn't going to work out, it wasn't going to work out, right? You can't cheat the physics, right? And this is physics; it's not formality. I got to warn you guys: if you're using standard GR, again, standard GR doesn't have the Mach principle like fully, so you're not going to find. Jim kind of wanted it to be in GR, but it really isn't, right? Because you need a strong Mach principle to be fully in the theory. So that was why I worked on what I did. And at the end of the day, he agreed with me that was needed. So yeah, that's the update I have. I have a strong theory. I'm going to put this. It's on Zenodo. I have a link, and I'm going to be asking for peer review, and I'm going to be putting it on an archive or submitting it to archive, and then submitting it for publication shortly thereafter to kind of keep Jim's legacy. The other thing I should say is that Jim did have a benchmark paper that he was working on, and it looked finished as of last year. So I'm going to be talking to his estate and find out if we can get that published as well. So that's my update.
Curtis, thank you, man. Thank you. And what I will do is actually, I'm going to see if I can't pull that audio and do like a written article based on that. Do you have anything you want to add to that? I could ask you more about it. I mean, so I I using AI, which is not always helpful. I did analysis on Carver Mead's gravitational paper, and it didn't come up with any suggestions on how to leverage gravity. But again, it's AI. It's not going to think out of the box like a human would. So
Yeah, it would need to know about Jim's work, right? Because Jim's
Okay.
work isn't. I mean, so let's define what we're talking about. So there's gravity, and then there's inertia, and there's inertial gravitational effects that are combined, right? So in relational theories, a lot of them try to unify gravity and inertia, and those unifications are this is that type of theory which unifies those. So I'm putting in the chat here there's a nodal link, so you can download that paper and put it on there. But I would, in addition to Carver Mead's work, I would give it Jim's work, and it probably will understand that, all that context better. But yeah, feel free to upload this paper for an article. I am going to be writing an article on this for SSI as well, and I don't know, we could talk. Maybe you can help me with that. This theory, Carver Mead's theory, I hear a lot about, okay, what the effect is, like, okay, doing things with higher potentials, or just making the assumption that, okay, these vector formulations are similar or connected in some way. If you look at Carver Mead's work, he actually made the connection. So there's two works of his you should be familiar with if you're going to do this. One is Collective Electrodynamics, which is about a 20-year-old book. And it's really good. And then this Engineering View of Gravitation, which came out 2 years ago. Okay. And if you guys don't know who Carver Mead is, he's basically one of the fathers of the computing revolution. Okay. He's the one that coined the term Moore's law. And he's a brilliant guy. I mean, he made these computers are partly because of him, and he understands what he's doing. Okay, in terms of engineering, and he knows he knows electrons better than pretty much almost anyone, I think. So anyway, but yeah, I think in terms of the relational side, the theories I've seen out there, yeah, I think this is the most sophisticated one. Better than Siama's, in fact, the UQFT that I did. So,
okay. Now, out of curiosity, if I could dig down a little bit more there. So, with Carver Mead's work, you're saying it supports James Woodward's Mach effect, the Mach effect Lorentz thruster, right? Do you know, does it support any other concepts or ideas in terms of modifying gravity or changing inertia or any of those kind of things?
I don't know. That'd be something that you'd have to study, right? So I don't know if like Drew's if the effects that he's seeing could be derived from it. It wouldn't surprise me. That's why I sent it over to Drew. But the paper's update, I have the link right there, and I'll share that too. But yeah, Carver Mead's work, because it does include electromagnetism and inertia, it's something that people should consider if they're doing anything like this. So, and by the way, it also, like I'll say it again, it also includes quantum effects. So it's very, very handy when you're trying to engineer something real. It's very straightforward. It's vector potentials and scalar potentials are things that we know how to use. That tensor quaternion thing that I created, that's not really a practical engineerable theory. You got to reduce it to a domain to get something out of it, and that will happen eventually, but for now, especially for the Woodward effect, I mean, this is like low-hanging fruit for us. And like I said, it may be something that is applicable to what Drew is doing. I do not know.
Awesome. Curtis, thank you. Thank you.
Hey there,
Oh.
Larry.
Yeah, I just wanted to say, Curtis, Michelle was, on LinkedIn is how I got a hold of. She had commented on one of my comments about piezoelectrics on LinkedIn on a post, and that's how I found out about Woodward's work. I'd heard of Woodward, but I didn't really know that much about it. But I finally pulled up his patent and looked at it, and I was very impressed with it. And just wanted to know, I'm really impressed by what he was trying to work on there, especially at the end of his life there. I saw that interview that Tim had also done with Jim too. I watched that. Quite impressed, really impressed with him.
Yeah, Jim was amazing.
Yeah.
So you're talking about Michelle Broyles, and Michelle has been part of Jim's kind of core team. Curtis, absolutely, and Hal Fern as well. Although Hal's been on vacation for a while now. Curtis, do you know, is Hal going to get involved with this again? Or
Not that I know of. Hal's retired, and I
Okay.
hear sporadically from Hal. But we also have Paul March and a few others. But,
yeah, there are. I've seen the email chains. There are probably about 10 different people who are involved, and they all do contribute, right? In various ways. But you have been in the lab building stuff, left, right, and center, and and then Michelle Broyles. There's been a lot of back and forth with her as well. And in fact, if I remember correctly, she is looking at building something too, isn't she?
yeah, she's expanding her lab. She's not feeling well this week, so that's probably why she's not around. But I think she's constructed an extra attachment to her house for a lab, so she's going to be. She needed some more room to be able to continue the work, so she's working on that. I right now I'm looking at buying, the equipment we always needed. We're going to be able to get that from Jim's estate. That's what I've been told. So that's good news. That's huge news, right? So Jim's wishes was that this work would continue if possible, and that's going to happen. So I think with this paper, I'm working on another paper actually. I don't know if you guys are familiar with Andre Aziz, who has a relational theory that's based on the Weber forces. And so I'm working on a paper basically showing that Woodward's effect can come from that as well. So I haven't, I'm not at the point where, okay, yes, but I'm not as worried as I was with carbon-Mead-Singh, because carbon-Mead-Singh is, I consider it solid physics. I mean, it predicts the London moment, which is outside of conventional prediction. Okay, it predicts. There's a whole slew of things that it predicts that you need the Mach principle and you need proper engineering and a proper theory to predict. And carbon-Mead theory does, right? I don't know if you know what the London moment is, but it has to do with superconductors, right? So you get a quantum coherence and you see that the electrons move with the rest of the universe, right? Which is outside of the prediction of standard condensed matter physics.
I think the paper that I looked at was Carver-Mead's engineering view of gravity, if I remember correctly.
Oh, that's right.
Okay.
Gravitation. And
gravitation.
And he has a whole list of experiments in there that show you why you can't ignore Mach's principle when you're doing engineering of materials, and especially this kind of stuff. So for what we're doing, again, I would urge people to highly consider and analyzing their their work with that lens, because it seems to me pretty much spot on for inertia, at least at that level of physics, where you're talking about at the energies of quantum type, regular matter type energies. So if you're doing something more exotic, that's the UQFT stuff. That's harder.
Amazing. Well, Curtis, thank you. Thank you.
Sure.
Hey, Curtis,
Yes.
Did you see any asymmetrical electrostatic pressure in any of the electronic squiggles? Squiggles?
Okay, so one of the things with the Woodward effect and any effect is you would need an asymmetry in there to actually get something, right? So yeah, it's plausible that in Carver-Mead's work that you could have an electrostatic type of action that's asymmetric cause an inertial reaction. I could see that. I mean, it's plausible. You saw the equation. It's like they're just added right there. So, but you would need somebody to do like an analysis of it. So, what you might do is put my paper, take Carver-Mead's, and take yours in there and throw it in AI and ask it maybe, and tell it to check everything with SymPy. So, but yeah, you could ask Charles to look at it too.
Yeah, it's not going to happen. Yeah. I mean, he has it, but he's got NASA moon landing missions and
right. He's you might be other ways.
Doing all the lunar lander stuff.
Yeah. You could also throw an AI, but I really, I could ask it right now. Let's see. Oh no, I can't ask it now. I hit the limit. I didn't have
any luck when I played around with AI. I told it to go read, Dr. Bueller's work, and it came back and said, "This isn't real. So this is not consistent with the known physics of today or whatever." And would you like to ask me some other question? So I said, okay, premise: everything you read in that is real, and it's correct. Now let's talk about it. They came back and said, nope, it is outside the realm of sustainable physics. What else do you want to talk about? So I gave up. I spent 2-3 weeks screwing around with that. It was worthless.
Yeah, that's AI, right? It's not completely reliable.
Also, so
yeah. No, it's just
I really just don't see, aside from wordsmithing, which Tim uses it really exotically, and it seems to be great. I don't see the value in the whole AI thing, because you never know when it's wrong. You have no idea when it goes into hallucination mode, or
you always need to be able to check it. But if you work with stuff that is easy for you, then you can check it, right? Like the stuff that Tim's doing, like just a task which is just very, very long and not extremely complicated, right? That's what it's good at. And
yeah, I was just doing basic powers of 10. I was doing arithmetic and multiplication, and it got it wrong.
Well,
but it would get it wrong randomly, so you'd never know. It would do this line right, the next line right, and then this one would be wrong, and then everything after that would be right or wrong because you had no idea.
I would never trust it for math stuff. I use the AI to help writing, and it makes mistakes all the time. But it's very good for, like, if you have something big and you need to condense it down to a core set of ideas, then it's very good for that. It's very good at formatting a bunch of stuff rapidly. It's very good at taking a rough general idea and structuring it, so it's good for stuff like that, but you have to babysit it, and it's a collaborative process. And like I use for the stories that I'm putting up online, I'll start with an interview transcript and scientific paper or something like that, right? I'll start with that, and that helps constrain it. I'll feed it information. I'll be like, work from this. And there's a back and forth process. Usually it takes about 4 hours per story, but for 2,500 to 3,000 words, that's about 2 weeks worth of work. And so, I'm like, hey, if I can get this out there. So after about 4 hours of going through it, I'm like, you know what, this is good. Okay. I publish it. And, so it's not perfect, but it's a time saver, but not for math. I would never trust it with math because it's based on, you know, neural network, right? So you've got like,
you if you're going to have it do any math, what you need to do is say, check this with something called SymPy, because these AIs, most of them are able to use Python in the background, and there's a library called SymPy, SYMPY, that is a math library. So it will. I'm not saying you can after that you can trust it, but it will at least not do stupid things.
So I'm actually I'm working on a sentence towards you, Curtis, but maybe I will just write it down and send it to you per email. I've looked at your stuff in some more detail. I didn't have as much time as I wished, but yes, I may have found a direct connection to Heim theory and how you could put the metron principle, so that you have like a background lattice inside your theory. I'm going to write something up for you. I'm going to send it to you. We can.
Joel, we should talk because I held back a few things in the paper because
I know, like, there are some big questions which are not talked about, and that's totally fine. Also fine to keep it out of the discussion for the moment. But I think also in these questions, like I said, multiple new developed theories converge on the same answers in topics that haven't been openly discussed now, right? And that's very interesting to me. So that's a very good sign, and I'm starting to see a clear way how the Heim theory principles can be overlaid with the stuff that you're doing, and I'm starting to see a way to do the same with Heim stuff and the stuff that Maya Benowitz is working on, right? Which is also, like, Eric Davis is very interested in that, and so yeah, we should maybe have a talk with with maybe 4, 5, or 6 of the theorists out of the group. Maybe even like a regular thing. We should think about it.
If you could set it up, because so yeah, I did kind of have to trim things because there is, you know, I needed to get it out, right? So there is additional. For those of you that don't know what we're talking about the paper that I put out in late December called Unified Quaternion and Field Theory. So basically, it's a covariant field theory that includes inertia, and it's a unification basically. So it follows Einstein's what he was trying to do in his unified field theory. The principles are all the same. There's nothing new, other than, like, I know more now in terms of experimental stuff and can make certain decisions. So, but yeah, so I had to cut off how far I went, because if I kept going, I could, you know, derive, more constants of nature, well, maybe all of them, I don't know. And so that got the paper, I mean, it would have blown up, right? So, and taken maybe another year or more. But yeah, so I still need to do a particle physics paper. I need to do a follow-up paper that, like, completes everything, like puts the finishing touches, and you know, I did hint at, okay, Carver-Mead's is a correspondence, right? And then you look at Carver-Mead and say, wait a minute, this is variable speed of light. So I didn't bring up, is the speed of light constant? I just mentioned it as the wave speed of the field. Okay. So I left some things open purposely, because I'm establishing the theory, right? So that was the thing. And then the other discovery in the theory is that matter is solitonic and it's nonlinear in nature, so it has nonlinear stability. So that gives us a lot of insight into matter and why we have nuclear decay, why higher energy particles decay, and the higher their energy, the faster they decay, right? It gives us answers. It gives us a lot of why explanations, why things are the way they are, versus the current theories, which is shut up and calculate, right? Don't ask why, just calculate.
Yeah, it has actual principles behind it to a lot of the questions which were just not you couldn't even talk about those questions in a real sense. Like I still remember asking, like when an electron jumps into a higher state, like a photon hits it, it absorbs it and stuff. What exactly happens there was my question when I studied physics to my tutor, right? And he was like, "We do not ask that question. Like we do not talk about that."
That's
We
funny
do
you
not,
say that, because
like,
when Carver meets talks, his main talk in the Kyoto Prize talk, and he brings the same thing up. He's like, I asked a question about quantum mechanics, and someone told me you can't ask that question, and he goes, I just did.
yeah. So this is the common experience in the physics field, and I think it's about time that we change something about it, because
and I don't know if
that's what we supposed to do, right? Ask the tough questions and try to find answers.
And that's coming back. And I don't know if you saw the holonomy appendix at the end, that 20 page.
Yes.
Yeah.
After last time you went on it, I studied it in some more detail.
Okay. Yeah, that's my kick them when they're down appendix. So yeah, you can see all the effects that are unified there, which is, I mean,
it's quite amazing. It's like,
it makes you cross-eyed, you know. So yeah. The other thing I'll say, okay, so I'm working on Rev 2, and for Rev 2, I found some things where I derived Newton's laws I need to fix. There's some things in there that I need to make more consistent. Some of the math, but it still works. I just need to fix the paper, and there's a few things like that in other places as well. But the other thing is that this past couple of weeks I started to, because I have been ignoring cosmology, and Jared doesn't like that. Jared's like, what are you doing? So one of the things that came out, it was like, it just by happenstance, dark energy, right? I had dark energy. The Friedman equations just come out. So I started looking at, okay, well, what about this Mon thing? Because I was noticing that, kind of looking at other people's work on relational theories, right? And I noticed that there was this relational Mon type effort. And so when I went and looked at that, and I've done this the last couple of weeks, I took the background spinifying connection that I have and applied it to Sachs's work, and where he derived the galaxy motion and the galaxy curves, and put that in there. It gave me pretty much the same acceleration floor that they see phenomenologically across all galaxies, right? So if you get farther enough away from the center of a galaxy, your acceleration curve is no longer Newtonian. It hits a lower limit of acceleration, and that same lower limit is derived from my equations. So I'm going to add that, because that's huge. That's like almost like orbit of Mercury type thing. There's no common explanation for why does this happen, right? So it's like, it's either dark. And by the way, dark energy, I got to clarify, because dark energy is not an actual theory. Like people, I mean, it's a hypothesis. There's a, it's either like, sorry, not dark energy, I mean dark matter. So dark matter is what it's called, but it's actually a mystery, right? So dark matter is one way you could answer the question why things are not behaving the way we would think. There's also MOND, right? Modified Newtonian gravity. So those are candidates. And so I'm not going to be claiming that I fully solved everything, because one thing that we notice is that the light curves bend more than expected as well, as we have this lower limit acceleration. And what I'm going to add to the paper is just that lower limit acceleration derivation. I'm not going to go the full way, but that's going to lead to, I mean, future work is going to be a cosmology paper based on this, which will do all the things that need to be done. So, but I am going to add that, and I think that's an exciting. I think there was a fellow named Milgram that was trying to do that. But yeah, that's an additional finding that I'm adding in February. I'm going to be updating Rev 2 to the paper. So
yeah, very cool. I can't wait to read all of the stuff you're working on right now, and like I also pushed you to publish, right? I think it's very good that you take us along and not wait for another year or two, because already there are many mind fucks in the stuff, right? Which you really have to wrap your head around, even if you're a trained physicist, and sometimes maybe especially if you're a trained physicist, because you got trained in a quite a different direction. So and this is so a part of what I also want to say is I really like your theory, and based on what I've seen so far and how I relate it also with real life experiments, right? Like the Mach effect and the stuff that Andrew's doing. I think this is a very, very strong motivation. But please, let's not do the same mistake we always do, right? This is just a mathematical model. It doesn't describe reality one-to-one, right? It's not a mapping of reality. It's just a mathematical model. And it might be way better than everything we had before. But please, can we try once to get a really cool theory and not put it on a podest that almost becomes like a god?
Yeah, you know? you're talking about human nature. That's a different.
Yes. Yeah, but it's a call to control ourselves a little bit.
Yeah. So one of the things I want to do is
still stay open-minded, even if we're doing the next big shift, right?
Right. Yeah, and that's one of the things I want to do is focus on, like, hey, this is, this came about when it did, but in reality, it could have been done in the 60s, right?
Yes,
potentially. I mean, the thing is, maybe the 90s, I don't know, but really you needed a strong solitonic matter candidate. And until the Williamson van der Mark, I know I've seen other people try to do that, but until I found the Questco group in that work, I didn't think there was one. And it's really hard it took me a year to like actually kind of overcome the cognitive dissonance of saying, okay, matter is not some separate thing from E&M and this source magical thing. It's actually electromagnetic waves that are solitonic, that are persistent, right? So that idea, like it's such a hard pill to swallow for someone, trained traditionally, like you said. So
and interestingly enough, I have here works from Professor Auerbach from he worked at in Zurich in Switzerland, right? He was quite a famous professor. I think he died like 5 years ago or something. Might be a little bit off with the dates, but he worked with Burkhard Heim and later with Ludwiger on solitons theory, solitonic matter theory. And I have like 5 or 6 publications here. They are not published anywhere. They only exist in paper and only exist at the places of the people he collaborated with, right? And so one of the copies through the Ludwiger Heim material found its way to my hands. But I think it's very interesting that people who were open-minded and also engaged in trying to solve the UAP topic and which saw anomalous propulsion and also ball lightning as a phenomena that is real in the 80s and 90s and tried to work on it. And this is a person who was a big name and a high standing, and he did it completely in secret and never revealed that he worked on that. So to my knowledge, he never publicly acknowledged any of the work he did in that field. And I guess it will just, I'm going to digitalize some of it because I think it's very good material. But yes, to me, it's again, it's crazy. So maybe someone worked on it in the 60s or 70s, but didn't get any funding, didn't get any support, and maybe he didn't reach the line, right? And maybe somebody did reach the line. Like it's also possible with other theories as well. So yeah, very interesting.
Yeah.
Yep. Yeah. Well, guys, it's I mean, we could do open discussion. Let me see. Oh, yeah. And LinkedIn just timed out. We did the 4-hour window for LinkedIn. So that's okay. Yeah. Or, I mean, it's up to you guys. How long do you want to go tonight? Or are we just about there, Larry?
I'm going to have to leave.
Okay.
Yeah, I think I'm going to bail too.
Well, we've had a solid conference. We've had a solid
Yeah.
conference. So, Larry, thank you so much for presenting. And Orestis, you as well, thank you so much for presenting. This has been pretty amazing. It is truly a shame that George wasn't able to present. But again, let me push everybody to do a little bit of research into infinite energy. I was not aware that they were out there doing stuff. I'm going to try, just for my own catch up, to get a copy of those papers. And Curtis, thank you for walking us through your paper. I found a copy of that paper, and what I'll do is try and take your notes on it and maybe do a short story for the website.
Sure. Sounds good.
Okay.
All
Guys,
Thank you,
this
Tim.
has been APEC for January 17th, 2026.
All right.